The Milky Way presents itself as a barred spiral galaxy with a flat disk, a central bar and several major arms that wind outward through lanes of gas and dust. The Sun sits in a minor spur between two larger arms, a short bridge of stars and clouds that astronomers call the Orion Spur. Star formation is not uniform across this disk. It concentrates along the denser ridges of the spiral pattern where gas slows, piles up and cools enough to make molecules. In these long bands, giant molecular clouds gather and fragment, and young clusters like cavities in the gas that surrounds them. The Eagle Nebula belongs to this banded structure. It lies toward the inner side of the local quadrant of the Milky Way in the direction of the constellation Serpens and at a distance of roughly 7,000 light-years from the Sun. Its address in terms of galactic architecture is within the Sagittarius arm, which some maps name the Sagittarius-Carina arm. From the solar neighbourhood, the line of sight toward the Eagle Nebula runs close to the galactic plane, through crowded star fields and dark dust lanes that mark the mid-plane of the disk. This perspective places a large column of interstellar material between the observer and the nebula, a circumstance that shapes how the region looks in different wavelengths and how its true structure is measured. The larger setting around the Eagle Nebula is a complex of gas and young stars collected along this segment of the spiral arm. Spiral arms are not rigid objects. They are patterns that move through the disk and organise the flow of material. Gas that enters an arm slows slightly relative to the pattern and compresses much like traffic that bunches on a gradual highway bend. In the compressed zones, densities rise, temperatures fall, and molecules form on the surfaces of dust grains. Carbon monoxide becomes a tracer for the coldest parts of the clouds, and hydrogen binds into its molecular state in shielded interiors. Over time, gravity pulls clumps within these clouds toward collapse, and the first massive stars that form carve bright cavities of ionized hydrogen into the surrounding gas. The Eagle Nebula is one of these cavities, an H2 region, inflated by the radiation and winds from a young open cluster at its core. Seen in a wide view, the nebula sits among many similar objects along the same arm, each marking a place where the spiral pattern has gathered enough material to ignite new stars. The disk around this region carries a gentle gradient in chemical makeup from the centre of the Milky Way outward. The inner disk tends to hold gas enriched by earlier generations of stars, while the outer disk tends to be poorer in heavy elements. The Eagle Nebula occupies an intermediate radius where enrichment is moderate. This balance shapes the cooling rate of the gas, the abundance of dust, and the opacity of clouds to ultraviolet light. More dust means stronger shielding for molecules and a thicker veil along the line of sight. The mix in this sector supports the formation of large clouds with dense cold interiors and bright sculpted surfaces where young stars expose and heat the outer layers. Galactic rotation threads through the picture. Material in the disk orbits the centre on near-circular paths whose speed varies with radius. The spiral pattern interacts with this rotation to produce regions of compression and shear. Compression along the arm promotes cloud assembly. Shear across the arm can stretch structures and limit the size of bound clumps. The Eagle Nebula sits where these two influences both matter. Over many millions of years, clouds drift into the arm-assembled spawn clusters and bubbles, and then drift onward as their gas disperses. The nebula is part of this cycle, not a permanent fixture. Its present shape records the current balance of pressure from hot ionized gas inside the cavity, and the weight and structure of the colder material just beyond its rim. Outward from the arm, broad voids of lower density gas open between ridges. Inward toward the galactic centre, the arm blends into the bar and into other crowded lanes where young clusters and hot gas are common. The Eagle Nebula's location along the arm places it near neighbours that share similar ages and conditions. Clustered star formation means that the radiation field in this sector is not only set by the stars within the nebula, but also by other young stars within the same arm segment. Their combined light leaks through channels in the clouds, adding to the background field that bathes the pillars and rims when viewed in detail. The vertical structure of the disk also shapes the wider environment. Gas and dust are concentrated toward the mid-plane, with densities falling off above and below. The Eagle Nebula lies near this midplane where the column of intervening material is thick, and the interplay between gravity pressure and turbulence is strongest. Supernova shocks from earlier generations of massive stars ripple through this layer and can compress clouds that later host new clusters. Over time, such shocks carve superbubbles and shells that expand, merge and seed new sites of collapse at their edges. The arm segment around Serpens carries evidence of these nested shells, and the Eagle Nebula sits along an arc that aligns with larger scale fronts in the region. This placement matters because the pressure in the surrounding medium sets how fast ionized cavities expand and how easily radiation and winds sculpt the cloud surfaces. From a measurement point of view, the outer context controls what is seen and what is hidden. Optical images record starlight and the bright lines from ionized gas at the nebula surface, but are strongly affected by dust that absorbs blue light. Infrared maps trace warm dust and bring forward the stars forming inside the cloud that are invisible in visible light. Radio observations track the cold molecular gas that outlines the mass reservoir from which stars form, and they measure velocities along the line of sight that reveal how the gas is moving within the arm. X-rays find very hot gas from shocks around massive young stars and from the combined winds inside cavities. Placed together across the scale of the arm, these windows show a sequence of cloud assembly, star birth, and gas dispersal that repeats along the spiral pattern. The Eagle Nebula is a single scene within that repeating sequence. Its outer surroundings also fix the timescale for how long such a scene lasts. Spiral arm crossings for individual clouds and clusters span many tens of millions of years, but the bright phase of an H2 region endures for a much shorter time. Once massive stars have formed their ultraviolet light, quickly ionizes nearby gas and drives pressure fronts into the surrounding cloud. The cavity grows on a timescale of a few million years, while the most massive stars live only a few million years before ending their lives. The Eagle Nebula is in this bright short phase at present. It also sits in a part of the arm where earlier generations of stars have already enriched the gas, which means molecules and dust are plentiful enough to shield cold interiors while still allowing strong surface heating and erosion where the cavity meets the cloud. The geometry of the view from the solar system adds one more layer. The line of sight passes through multiple spiral features and through widespread diffuse emission that fills the plane. Bright stars in the foreground and background share the same sightline as the nebula. Careful separation of these components relies on distances derived from parallax for nearby stars on the colours and magnitudes of clusters, and on the kinematics of the gas measured in radio lines. In this way, the Eagle Nebula's placement within the Sagittarius arm is established, and its relationship to neighbouring clouds and clusters is mapped in 3 dimensions, rather than as a 2-dimensional projection on the sky. The outer setting thus becomes a scaffold on which the details of the nebula can be hung. In summary form, the galactic context of the Eagle Nebula is a star-forming corridor along a spiral arm of the Milky Way where gas is concentrated, cooled and assembled into giant molecular clouds. Young clusters within this corridor inflate cavities of ionized gas, and one of those cavities is the Eagle Nebula. The environment supplies the raw material, the external pressure, and the background radiation that shape what is seen at the next scale inward. It fixes the timescales on which clouds survive, clusters light up and cavities expand. It sets the chemical and dynamical conditions that decide how dense structures resist or yield to erosion. With the arm, the plane and the larger complex now described, the scene is set at the outermost level. All later detail will remain inside this map, moving step by step inward from the spiral corridor to the specific nebula, and then to the smaller structures that it contains without leaving the frame, established by the Milky Way's disk, and the banded pattern that guides the flow of gas and the birth of stars along its length. Along the Sagittarius Carina arm, the disk's orderly rotation meets a slowly moving spiral pattern that gathers gas and dust into a denser lane. A spiral arm in this context is a kinematic pattern rather than a rigid structure. The pattern rotates with a characteristic speed called the pattern speed, while gas and stars orbit the galactic centre at speeds that vary with radius. Where the difference between these two motions is favourable, material drifts into the arm lingers and compresses. The result is a ridge of enhanced density that runs for many thousands of light years, with a width of a few hundred light years, that broadens and narrows as local conditions change. The arm does not trap matter permanently, it organises flow. Clouds assemble within it, form stars, and then the gas and the new stars move onward as the arm's pattern continues. Gas entering the arm feels a gentle gravitational tug toward the ridge, and a change in pressure as it meets material that arrived earlier. The flow slows slightly with respect to the pattern, and steepens into a compression. In cold phases of the interstellar medium, even modest compression can raise density enough that cooling begins to outrun heating. Cooling proceeds through atomic lines at first and in well-shielded zones through molecules and dust emission. Temperatures fall from the warm neutral phase into the cold neutral phase, and with further shielding into the molecular phase in which hydrogen binds in pairs and carbon monoxide becomes a tracer. As temperature drops, thermal pressure decreases and allows gravity to gather matter more efficiently. The sequence is not uniform along the arm. Small shocks variations in magnetic field strength and the imprint of past supernova shells modulate where and how strongly compression acts, so that the arm alternates between segments rich in molecular clouds and segments where gas remains mostly atomic. The large-scale shear imposed by galactic rotation shapes the assembled structures. Shear is the differential in orbital speed from one radius to another. It stretches clouds along the direction of rotation, and can prevent the largest agglomerations from remaining bound unless self-gravity and pressure support balance the tearing tendency. In the Sagittarius Carina arm shear is strong enough to elongate young clouds into filaments, yet not so strong as to erase them outright. Magnetic fields thread the gas and provide additional support aligned with the filaments channeling flows and moderating fragmentation. Turbulence stirred by earlier generations of massive stars adds random velocities that both seed and resist collapse. The net effect is a patchwork of long filaments, knots and clumps, some drifting towards self-gravity, others held near balance by pressure and shear. Streaming motions accompany the arm. As gas moves through the spiral potential, it deviates slightly from a perfect circular orbit. The deviations create characteristic offsets between traces of different phases. Atomic gas often leads the arm on the side where material first compresses. Molecular gas piles closer to the midline. Ionized gas and hot dust light the downstream edge where young stars have formed and begun to erode their birth clouds. In the sector that hosts the Eagle Nebula, these offsets appear across the sky as parallel lanes, with dark dust features tracing the cold midline and bright emission marking zones where ultraviolet light has carved cavities. Measured velocities of the gas in radio lines record these streaming patterns and provide a three-dimensional context in which individual nebulae occupy specific niches along the arm's flow. Chemical composition varies gradually with galactocentric radius. Closer to the centre, gases cycle through more generations of star formation and tends to carry a higher fraction of heavy elements. Farther out, the gas is more pristine. The Sagittarius Carina arm at the Eagle Nebula's radius sits on the intermediate part of this gradient. The mix of elements controls dust abundance, and thus the shielding depth for molecules. It also influences how quickly gas cools after compression. In this sector, enrichment is sufficient to support robust molecule formation and abundant dust, yet not so high as to quench ultraviolet penetration completely. The balance favours the development of large molecular complexes with cold interiors and sharply illuminated rims where young clusters heat and ionize exposed surfaces. The arm hosts multiple generations of star formation in close proximity. Massive stars born earlier drive winds and ionizing radiation that evacuate bubbles in the surrounding gas. When such bubbles collide or expand into denser ridges along the arm, they compress gas at their edges and concede new regions of collapse. This coupling does not proceed in a single direction. In some places, the removal of gas by winds and radiation inhibits further star formation by dispersing the raw material. In others, pressure waves along bubble walls collect matter that later collapses. The arm's appearance as a chain of bright cavities, dark filaments and scattered young clusters reflects this balance of dispersal and trigger. The Eagle Nebula lies within one such chain, but the present focus remains on the corridor as a whole rather than on a particular cavity. Vertical structure across the arm affects both visibility and dynamics. Gas is densest near the galactic midplane and thins with height. The scale height depends on temperature and turbulent support. Cold molecular gas hugs the plane more tightly than warm atomic gas. Supernovae lift hot gas into a thicker layer, forming chimneys and fountains that vent energy upward, and later rain cooled material back toward the plane. Where the arm intersects these vertical flows, the pressure near the midplane can rise, assisting compression at cloud surfaces. The same flows sweep dust into arcs that increase extinction, along certain longitudes, shaping the observed contrast between dark lanes and bright emission. The pitch angle of the Sagittarius-Carina arm sets how sharply it winds around the galaxy. A modest pitch angle, as in this arm, produces a gentle spiral rather than a tight coil. This geometry influences how long a given cloud experiences arm conditions. A gentle angle spreads the compression over a longer path length, allowing extended cloud assembly and prolonged exposure to the pattern's influence. The corrotation radius, where the pattern speed matches the orbital speed, lies at a different galactocentric distance than this sector. Being away from corrotation means the gas overtakes the pattern, or the pattern overtakes the gas, ensuring that material passes through the arm rather than remaining co-moving. The observed sequence of atomic to molecular to ionized features along the arm is a consequence of this passage. Within the arm, the interstellar medium occupies several thermal phases at once. Warm ionized gas fills cavities around young clusters. Warm neutral gas permeates diffuse regions. Cold neutral clouds bridge to the denser molecular phase. Magnetic pressure and cosmic rays contribute to the total support, especially in diffuse components. The balance among these pressures determines how sharply an ionization front advances into a cloud and how effectively a shock propagates along a filament. In the Sagittarius-Carina corridor, typical pressures are high enough that ionized bubbles expand at speeds of a few kilometers per second in their early stages, and then slow as they sweep up mass. Such expansion shapes the arm by carving channels through which radiation and winds can reach deeper layers, creating the sculpted edges that later appear as pillars and ridges at smaller scales. Kinematics recorded in molecular lines show that the arm hosts cloud-cloud collisions and converging flows along filaments. Where two streams meet at low relative speed, densities can climb efficiently without disruptive heating. Such meetings are more likely along the arm's spine, where multiple filaments intersect. The outcome is the formation of large clumps with masses sufficient to form clusters that include massive stars. Those stars, once formed, quickly change their surroundings by ionizing and heating gas over parsec scales, a process that begins the transition from a dark cloud to a bright nebula complex. Although individual collision events are local, their frequency is modulated by the arm's global dynamics, which regulate the supply of gas and the directions of flow. Observational windows along the arm must be coordinated to recover this structure. Hydrogen emission in radio reveals the widespread atomic component and traces broad kinematic patterns. Carbon monoxide maps delineate the cold molecular reservoirs and identify filaments and clumps. Infrared imaging finds warm dust in photo-heated rims and young stars still embedded in their envelopes. Optical imaging presents the bright lines from ionized gas, where dust lanes are thin enough to permit a view. X-rays register the hot plasma inside larger cavities and the energetic effects of winds and recent supernovae. Together they sketch as a corridor in which matter cycles from diffuse gas to cold clouds, to young clusters and back to diffuse gas guided by the spiral potential and stirred by feedback. Timescales along the arm are layered. gas spends many tens of millions of years orbiting the galaxy at this radius. A cloud may spend a smaller fraction of that time within the arm pattern, long enough to assemble, fragment, and form stars. The bright phase of ionized regions around massive clusters lasts only a few million years. The arm thus carries both long-lived scaffolding and short-lived lights. The scaffolding is the kinematic ridge that persists as the pattern moves. The lights are the H2 regions and luminous clusters that turn on and fade as each generation completes its earliest phases. Within this corridor, the pressure of the ambient medium sets how cavities expand, how far ultraviolet radiation penetrates into cloud surfaces, and how sharply shocks compress the gas. Regions with higher ambient pressure produce thinner, denser ionization fronts and sharper rims. Regions with lower pressure allow broader transition zones and slower erosion. The Sagittarius-Carina arm shows both regimes in different patches, reflecting variations in local gas supply magnetic field geometry and the recent history of stellar feedback. In either case, the essential behavior is consistent compression. In the arm facilitates molecule formation. Dense structures collect. Young clusters ignite. Radiation and winds carve the surfaces, and gas either disperses or is recycled into the next generation of clouds downstream. The Eagle Nebula occupies one site within this organized flow. Its presence indicates that the local balance in this part of the arm has already produced a young cluster, able to light and ionize its surroundings. Before turning to that specific cavity, the arm must be understood as the environment that supplies gas and sets boundary conditions. The corridor's gravitational pattern focuses inflow. Shear and magnetic fields shape filaments. Turbulence and feedback introduce structure. Chemical gradients fix shielding and cooling. Streaming motions set off sets between phases. These ingredients combined form the outer frame inside which any single nebula must be read. With the arm's address established, the path can proceed inward without changing the frame or the pace. The next region is the ionized cavity that defines the Eagle Nebula as an H2 region, a zone of warm, low-density gas surrounded by colder, denser material along the arm. The details of that cavity, including its cluster and its expanding shell, sit entirely within the corridor, just described and inherit its pressures, flows, and chemical mix. The description remains anchored to this setting as it narrows from the long spiral lane to the particular nebular volume, where those general rules express themselves in a single bright scene. The Eagle Nebula takes shape as a bright cavity of ionized hydrogen, carved inside a larger complex of cold molecular gas and dust, a pocket of warm, low-density plasma, surrounded by colder, heavier material that still resists erosion. As a whole, it is a textbook example of an H2 region, a zone where ultraviolet light from young massive stars strips electrons from hydrogen and holds the gas at temperatures near 10,000 Kelvin. The central source of energy is the open cluster NGC 6611, a loose congregation of hot luminous stars whose radiation and winds define the cavity's pressure and outline. The cluster's most massive members emit large numbers of ultraviolet photons. Those photons penetrate the surrounding gas until they are absorbed, creating an ionization front that wraps around the cavity and marks the place where warm glowing plasma meets neutral material. The shape is not perfectly spherical. It is lopsided and sculpted because the parent cloud is uneven, and because prior episodes of star formation have already created shells and channels that guide the flow. In visible light, the cavity shines in the red line of hydrogen and in the green and blue light from doubly ionized oxygen and singly ionized sulfur, each tracing layers of temperature, density, and ionization that together paint a relief map of the boundary. In infrared light, the dust at the inner edge glows with gentle warmth and deeper. Within the cloud, the younger stars still wrapped in their envelopes appear where the optical view remains opaque. Radio maps outline reservoirs of molecular gas just beyond the bright rim, confirming that the cavity sits inside a much larger store of cold material that continues along the spiral arm. The pressure inside the cavity is set by the temperature of the ionized gas, and by the momentum deposited by stellar winds from the cluster's hottest stars. Warm electrons and protons collide and push outward. Winds add a faster, more tenuous component that can inflate a hotter bubble inside the broader ionized zone. Where these flows hit denser pockets of gas at the boundary, shocks form and compress the surface layers. The ionization front advances into the cloud, where density is low, and stalls where density is high, leaving behind a ragged edge of bright rims, globules and pillars that point away from the cluster like shadows in reverse. Along this edge, a narrow layer called the photodissociation region forms. In that layer, ultraviolet light is strong enough to break apart molecules, but not strong enough to fully ionize hydrogen. The layer cools by emitting characteristic lines of carbon and oxygen, and by the soft glow of warmed dust grains, marking a transition from warm plasma to cold molecular gas. The location and thickness of this layer depend on the balance between incoming radiation and the shielding provided by dust and gas. It is there that much of the chemistry of the interface proceeds, setting the initial conditions for any new collapse that may follow compression. The cavity expands because pressure inside exceeds pressure outside. At first, the expansion is swift, then it slows as swept-up gas accumulates in a shell around the rim. If the shell meets a pre-existing channel, or a steep density gradient in the parent cloud, the hot interior gas can vent through the opening. This state is often described as a blister, where the ionized region breaks out toward lower density surroundings. In such places, the flow of ionized gas away from the nebula becomes a gentle wind called a champagne flow, a steady outpouring that carries ionized material into the broader arm, while the denser clumps at the rim hold their ground for longer times. The Eagle Nebula shows signs of this behavior with filaments and arcs that open toward one side, and with a rim that looks sharper and brighter where the cloud remains thick. The asymmetry records both the internal physics of expansion and the external structure of the cloud, which contains filaments aligned with the arm and remnants of older shells that predate the cluster now in view. At the heart of the cavity, the open cluster sits slightly off-center, another sign that expansion and erosion are not uniform. The cluster's age is only a few million years young enough that its most massive stars still shine, and old enough that their radiation has cleared the immediate surroundings. The stellar population includes a range of masses from hot blue stars that dominate the ultraviolet output and shape the nebula down to lower mass stars that contribute little to ionization, but will later populate the field with long-lived suns. The brightest members generate strong stellar winds that collide with each other, and with the interior gas-heating pockets of plasma to temperatures of many millions of degrees Kelvin. X-ray observations detect this hot component and show where wind-wind collisions and wind cavity interactions are depositing energy. The hot gas helps maintain the pressure that drives expansion, but remains confined by the denser shell that the nebula has swept up from the surrounding cloud. The boundary zone is where the most dramatic textures appear. Dense knots cast shadows into the cavity, and the shadows protect tails of material from direct radiation. The protected tails become pillars, long dark columns that point toward the cluster. Their tips face the ionizing light and develop bright curved caps where the surface is heated and evaporated in a slow stream called photoevaporation. Gas flows off these caps into the cavity, while radiation and shocks from the front compress the clumps just behind the caps. In some knots, gravity gathers the compressed gas into dense cores that can begin to collapse toward a star formation, while in others the erosion wins and the structure thins and disperses. The variety across the rim, from smooth arcs to jagged projections, reflects different local starting densities, different alignments with the radiation field, and different histories of shock passage from earlier events. Measurements of density and temperature across the region come from the brightness ratios of emission lines that respond to collisional processes in the gas. Closer to the cluster, where ionization is higher lines from more highly ionized species dominate. Farther out, the spectrum shifts toward lines that mark cooler, less ionized gas. These gradients help define the three-dimensional shape of the cavity, even when projection makes the shape look confusing in a flat image. Velocity information from spectral line profiles adds a second clue. Small shifts in wavelength reveal whether gas is moving toward or away along the line of sight. Combining such shifts across the face of the nebula allows a rough kinematic model of the expansion, a shell that grows at a few kilometers per second near the dense rim, faster in lower density corridors, and with localized accelerations where winds punch into denser patches. The Eagle Nebula's designation as Messier 16 ties it to the historical catalogue of bright diffuse objects in the Milky Way. That catalogue registers the bright ionized heart rather than the cold reservoir around it. Radio maps of carbon monoxide and other molecules show that the ionized zone occupies only a small fraction of the total mass of the parent cloud. Most of the mass remains hidden in cold filaments and clumps that extend beyond the optical nebula and supply material to areas of continuing star formation, not immediately illuminated by the central cluster. This layering explains why infrared images of the region reveal many more young stellar objects than visible light does. Stars in their earliest phases bury themselves in dense envelopes that absorb visible light and re-radiate the energy in the infrared, and disks around forming stars cast silhouettes against the bright background, even as their interiors remain cold and dark. The radiation field from the cluster does not end at the edge of the H2 region. It leaks through gaps and along channels into the surrounding cloud, heating dust and altering chemistry at distances far beyond the visible rim. In these outer zones, molecules that are fragile under ultraviolet light are destroyed, while more robust molecules survive in the shadowed interiors of filaments. The distribution of surviving molecules maps the balance between shielding and exposure. Observations find that this balance is patchy, with some lines of sight showing strong molecular signatures, and others showing only atomic gas, a pattern that in turn reflects the clumpiness of the cloud and the history of shock compression and dispersal along different paths. The region evolves on timescales set by the lifetimes of the massive stars that drive it, and by the rate at which the boundary erodes. Massive stars live only a few million years, after which they end their lives in violent explosions that inject new energy, momentum, and heavy elements into the surrounding medium. Before that final phase, their steady radiation and winds gradually hollow the cavity and eat into the cloud. The boundary moves inward where resistance is weak, and stalls where clumps are strong. The net result is a changing perimeter that reveals new layers of structure over time. Embedded young stars along the rim may emerge as their envelopes are photoevaporated, adding to the visible cluster, while embedded cores may fail to form stars if erosion removes their mass too quickly. In this way, the Eagle Nebula presents both birth and dispersal at once, a single scene, in which gas is assembled into stars in some places, while in others, gas is returned to the diffuse medium for future cycles along the arm. Within this overview, the important point is frame. The Eagle Nebula is not an isolated object. It is one cavity within a corridor of cloud and cluster along the spiral arm. The cluster that lights it is part of a recent generation of star formation in this sector and its radiation field, and winds inherit ambient pressure, magnetic geometry, and chemical mix from the larger environment. The cavity's expansion depends on the surrounding density, and its rim records the upstream history of the cloud. The nebula's visible brightness is only the surface expression of deeper processes that extend into the cold interior and outward into the diffuse arm. Every bright ridge, dark column, and faint arc registers this coupling between inner and outer scales. With the region now defined as a warm cavity driven by a young cluster and bounded by a sculpted interface with a larger molecular cloud, the path can narrow again, moving from the general cavity to the detailed behavior of the ionized shell and the pressure fronts that set the shape and pace of erosion across the surrounding material, while remaining inside the same setting and the same rules that describe the corridor and the nebula together. Ultraviolet light from the young cluster floods the surrounding gas and sets up a sharp boundary between ionized and neutral material. Inside, the boundary atoms of hydrogen are stripped of their electrons, and the gas settles at a warm temperature set by the balance between heating by energetic photons and cooling by emission lines from common elements. Warm gas has higher pressure than the colder material beyond the boundary, and that pressure drives the boundary outward as a shell. The expansion is not a single wave, but a layered structure. Closest to the stars lies a hot, tenuous wind zone, where the fastest outflows from massive stars collide and heat to very high temperatures. Beyond that zone fills the main body of the cavity a sea of warm ionized hydrogen, threaded by magnetic fields and seeded with small density variations. At the edge sits a narrow front where ionization falls rapidly, and where photons that remain after crossing the cavity are finally absorbed. Just beyond the front stretches a thin layer that is not fully ionized but also not fully molecular, a chemical transition zone that cools through fine structure lines in the glow of warm dust. Outside that layer, the cloud returns to the cold molecular state that stores most of the mass. The front advances in two related ways. Radiation eats into the neutral gas by stripping electrons from atoms, and pressure from the warm interior pushes on the front mechanically. Early in the life of the cavity, ionization outruns motion because the surrounding gas has not yet been stirred, and the photons can sweep through pores and low-density channels to create a larger ionized volume quickly. The front at this stage is said in technical language to be radiation-dominated. As time goes on, recombination within the ionized gas becomes important. Electrons and protons meet and reform neutral hydrogen at a steady rate that increases with density. The cluster's photons must replace those lost atoms to keep the gas ionized. When replacements just balance recombinations, the ionized volume reaches a temporary equilibrium. Pressure now takes over as the driver of growth. Warm gas expands against the cold cloud, sweeping material into a shell that thickens with time. This phase is gas pressure dominated. The front advances at a few kilometers per second, where the cloud is diffuse and slows to a crawl against dense clumps. The shell itself is not uniform. Where the parent cloud holds filaments or knots, the pressure wave wraps around them and piles gas along curved surfaces. Where the cloud offers a lower density corridor, the shell runs ahead, and the front bows outward. The combined action produces scalloped rims, bright arcs, and narrow protrusions. Within the shell, shocks appear wherever the outward push exceeds the speed at which information about pressure can travel. Shocks heat and compress the gas. Then the gas cools rapidly by emitting light in characteristic lines. The result is a thin, dense skin just beyond the sharp radiative boundary. That skin can become unstable in places where inner pressure, outer gravity, and curved geometry combine, allowing ripples to grow into ridges and troughs. Over time, the shell fragments into beads and folds that later read as knots along the rim. Radiation pressure contributes a smaller but non-zero share to the driving force. Ultraviolet photons carry momentum. When they strike dust grains or are absorbed in the gas, they transfer a push outward. In regions very close to the hottest stars, this push can matter, especially where dust is abundant and the gas density is high. Farther out, thermal pressure from the warm ionized gas remains the main agent. Stellar winds add a distinct component by blowing low-density cavities inside the larger bubble. Where multiple winds collide, they build a hot core with temperatures of many millions of degrees Celsius. The hot core leaks energy to its surroundings through conduction, turbulent mixing, and small holes punched in the inner wall. As it vents into the main cavity, it helps sustain the pressure gradient that keeps the outer shell moving. The geometry of the parent cloud sets where the shell breaks out. If the cloud is steeply stratified with density dropping toward one side, the front reaches that side faster. When the shell opens there, the interior gas streams away as a gentle pressure-driven flow into the ambient medium. This escape lowers the interior pressure and slows the advance of the front along the denser sides, producing a lopsided cavity. Observations of the Eagle Nebula show curved rims brighter on one flank and open filaments on another, consistent with a partial breakout into a lower density environment. Sightlines that pass through the breakout reveal a mix of warm ionized lines and faint high excitation features from gas that has been given more room to expand. At the contact between ionized and neutral gas chemistry changes quickly. Molecules that cannot endure strong ultraviolet light disintegrate in the first layer beyond the front. More robust molecules survive deeper in the cloud. Dust grains heat to temperatures of a few tens of degrees Celsius and radiate in the infrared, painting the boundary as a bright warm ribbon in those wavelengths. Small grains and complex hydrocarbons glow in specific bands where ultraviolet light knocks electrons loose and the grains relax by emitting photons. These signals trace the outline of the front even where visible light is blocked by dust along the line of sight. Radio observations of carbon atoms in low ionization states also mark the transition zone, providing density and temperature diagnostics without heavy extinction. The shell transmits pressure into the cloud through slow shocks. A slow shock raises density without raising temperature to destructive levels, allowing the compressed layer to cool and thicken. In places where pre-existing density peaks sit just inside the front, the extra pressure can tip them over the threshold for gravitational collapse. In other places, the same pressure strips mass from the surface faster than gravity can gather it, delaying or halting collapse. The balance between these opposing outcomes depends on the size of the clump, its internal turbulence and magnetic support, and the speed and duration of the external push. Along the rim of the Eagle Nebula, both regimes appear. Some caps thin and leave only long tails of dust and gas. Others hide denser knots that survive repeated sweeps and become seeds for later stars. Shells that thicken as they expand can develop thin layer instabilities. A small ripple focuses gas into a crest, the crest grows denser, and downstream material prefers to flow around it, deepening the trough on either side. The result is a periodic chain of bright knots on the rim. Gravity may help these knots collect more mass. Magnetic fields can either stiffen the layer against corrugation or guide the corrugations along field lines, aligning the pattern with the larger grain of the cloud. These effects are subtle and unfold over hundreds of thousands of years, a long duration compared with human life, yet a short slice of the bright phase of the cavity. They imprint the rim with a memory of both the external drive and the internal skeleton of the cloud. Measurements across many wavelengths anchor this picture. Ratios of bright optical lines from oxygen and sulfur respond to electron temperature and density, and map how those quantities change from the cavity center to the rim. Radio recombination lines from hydrogen measure velocities and confirm outward expansion. Infrared imaging shows where dust at the front is warmest and where the transition layer is thickest. X-ray data reveal pockets of very hot gas where winds collide. Together they chart a pressure ladder from the hot wind zone to the warm ionized body, to the compressed shell, and into the cold cloud. Each rung is linked to the next by a balance of forces that at any moment keeps the front in motion or holds it in place. The energy budget evolves as the most massive stars age. While they shine, their photons substitute for recombined atoms and keep the gas ionized. Their winds maintain the inner pressure. When one of these stars ends its life, the shock that follows adds momentum to the shell and can punch through weak sections. Over very long times, as the cluster's most luminous members fade away, the photon supply drops. Recombination then gains ground. The cavity dims and the front recedes unless other stars take over the role of maintaining ionization. The Eagle Nebula sits at an age where several bright members still support the shell and its advance. In this phase, the front exposes deeper layers of the cloud along one flank while it lingers against denser ridges along another. The dynamics also depend on the ambient pressure in the arm segment. A high surrounding pressure confines the cavity more tightly, producing a smaller bubble with sharper rims and higher densities at the front. A low surrounding pressure allows broader expansion and a gentler gradient across the shell. The sector that hosts the Eagle Nebula shows both modes in adjacent fields along the arm, and the nebula's specific outline reflects the local mean where it formed. The continuing arrival of external flows along the spiral corridor further modulates the shell. Fresh material drifting into the region from the arm's spine feeds the outer cloud and can thicken the shell on one side while the breakout continues on the other. Within the cavity, small clumps of dust and gas survive for a time as silhouettes against the bright background. They are eroded by streams of atoms that flow off their sunlit faces. The flow rate depends on the photon flux and the size of the clump. Large clumps develop stable photoevaporating caps with comet-like tails that point away from the cluster. Small clumps shrink rapidly and vanish into the ionized sea. These local processes ride on the broader front, adding fine texture without changing the overall push. Their lifespans are short compared with the age of the nebula, yet they record the ongoing conversation between light and matter at the interface. The ionized shell is thus the mediator between the driving cluster and the cold reservoir. It carries pressure outward sets where the front brightens and where it stalls and tunes the profile of density that the next layer inward will inherit. It advances in steps controlled by recombination cooling and the inertia of the swept-up gas. It breaks where the cloud thins and thickens where the cloud is strong. It ripples under the combined action of curvature, gravity, and magnetic tension. It glows where electrons collide with ions and with atoms, and it cools by giving light back to space in a spectrum that records its state. Seen at any single time, it is a mapped surface. Followed over time, it is a moving contour that reveals the structure of the cloud by how and where it yields. Keeping within the established frame, the description remains inside the cavity and its bounding shell, with all forces and flows inherited from the spiral arm environment already set. The next inward step stays with the boundary, but focuses on the fine-scale behavior of the front as it encounters denser remnants of the parent cloud, where shielding erosion and compression turn smooth rims into columns and knots without leaving the regime of ionization and pressure that dominates this level of the scene. Beyond the bright rim, the parent molecular cloud extends as a cold, dense reservoir that feeds the nebula's edge and sets the conditions for new stars. In this zone, hydrogen binds into molecules, and the temperature falls to only a few tens of degrees above absolute zero. Dust grains mixed with the gas absorb and scatter ultraviolet light, creating deep layers where radiation weakens and chemistry changes. Carbon monoxide forms and becomes the principal tracer, used to map the cloud in radio wavelengths. The bulk of the mass resides in hydrogen that is invisible to most direct observations, so the structure is read through the light of carbon monoxide and other molecules, through the faint glow of dust warmed by distant stars, and through the silhouettes that dust casts against the brighter background nearer the cavity. The cloud is not uniform. It is a hierarchy of structure with long filaments, embedded clumps, and smaller cores, each with its own density, temperature, and level of internal motion. Turbulence threads the gas, adding random velocities that broaden spectral lines and support the cloud against gravity on large scales. Magnetic fields pervade the material and couple to charged particles in the gas guiding flows along preferred directions and resisting compression across field lines. Together, turbulence and magnetic pressure limit the rate at which gravity can gather matter and help set the sizes of the structures that survive erosion at the nebular boundary. Shielding by dust controls the transition from atomic to molecular gas. At the cloud surface, ultraviolet photons dissociate molecules and heat the gas. Deeper inside, where the dust has absorbed most of the ultraviolet light, molecules persist, and the gas cools efficiently. The result is a layered medium, a thin photodissociation skin that grades inward into fully molecular interiors. Temperatures drop, sound speeds fall, and the characteristic mass scale for gravitational instability changes. Astronomers summarize that threshold with a simple idea called the gene's mass, the minimum mass that a region of gas must have to overcome pressure and begin to collapse under its own gravity given its temperature and density. In cold, dense interiors, the gene's mass becomes small, allowing modest clumps to approach instability if other forms of support do not intervene. In warmer, more diffuse layers, the threshold is higher and collapse is less likely. The parent cloud around the Eagle Nebula presents both regimes side by side because the cavity's light warms and erodes the surface, while the interior remains cold and shaded. Filaments dominate the cloud's mass distribution. They are long, narrow structures with widths of roughly a fraction of a light-year to a few light-years, and lengths that can span many light-years. gas flows along these filaments toward knots where filaments intersect. Observations of molecular lines record small velocity gradients along the axes of the filaments, consistent with gentle directed flows. Magnetic field measurements inferred from the polarization of dust emission often show fields aligned roughly with the filament length, or wrapped around the filament, indicating that the field both shapes and responds to the flow. Where several filaments converge, mass accumulates and forms clumps that can host dense cores. The clumps are colder and denser than their surroundings and show narrower line widths where turbulent support has partly decayed. These conditions favour further concentration, although not every clump proceeds to collapse. Some remain near balance, supported by residual turbulence or by magnetic tension that threads the gas. The cold interior contains a mixture of chemical species whose abundances depend on shielding and time. Simple molecules like carbon monoxide, ammonia, and formaldehyde trace different densities and temperatures. Deuterated species appear in the coldest, densest pockets, where ordinary molecules freeze onto dust grains and reactions favour heavy hydrogen. Ice mantles on grains incorporate water, carbon monoxide, and carbon dioxide. When dust is warmed by passing shocks or by nearby young stars, some of these ices evaporate and enrich the gas with new molecules. The chemistry provides diagnostics of recent heating and of the depth of shielding. In the parent cloud near the Eagle Nebula, maps show zones where molecules remain intact near the rim's shadows, and zones where dissociation has reduced their abundance, where the surface is more exposed. Pressure from the ionized cavity reaches into the molecular cloud as a slow shock that raises density in a layer just behind the bright rim. The increased density can push structures across the threshold into gravitational instability. At the same time, the boundary erodes the surface through photoevaporation, removing gas from exposed caps. Whether a given piece of the cloud collapses or disperses depends on its initial column density, its size, and the angle at which radiation strikes. Dense, compact knots with strong shielding can survive repeated sweeps and even gain mass as flows along filaments feed them. More diffuse protrusions thin and retreat. The variability in the rim's outline from smooth scallops to tapered columns records these differences. In places where the parent cloud is especially clumpy, the advancing front leaves behind strings of shadowed pockets that may later decouple from the surface and evolve as isolated globules. Internal motions inside the cloud span a range of scales. On large scales, turbulence maintains a cascade of eddies that transport energy from larger to smaller structures. On intermediate scales, gravitationally focused inflow along filaments reduces random speeds and narrows spectral lines. On the smallest scales within dense cores, thermal pressure and magnetic forces become more prominent relative to turbulence. Observationally, this progression appears as a relationship between measured line width and the size of the region being sampled. The smallest cores show the coldest temperatures and the quietest kinematics conditions that precede collapse. In the Eagle Nebula's parent cloud surveys in high-density tracers identify such cores along the filaments that feed the rim. Some lie fully buried, others sit just behind the rim where pressure from the cavity is highest. Magnetic fields regulate both support and fragmentation. If the mass along a field line exceeds a critical value, gravity can pull material inward despite the field's tension and pressure, especially when collisions between ions and neutral atoms allow the neutral component to drift slowly through the field in a process called ambipolar diffusion. In less massive strands, the field can delay or prevent collapse, and can guide the formation of elongated structures aligned with the field direction. Measurements near the Eagle Nebula's rim indicate ordered fields that follow the large-scale grain of the cloud, but bend around dense protrusions. This geometry supports the idea that pillars are denser relics shielded by their own mass, while the surrounding less dense material has been more easily ablated. Radiation from the cavity alters the chemistry and heating rate well beyond the visible rim, setting up extended transition zones where molecules are fragile. In these zones, carbon appears in a singly ionized state, oxygen remains neutral, and hydrogen is mostly molecular. Fine structure lines from carbon and oxygen cool the gas efficiently. Farther in molecules dominate cooling, and the gas reaches lower temperatures. Dust temperatures decline from a few tens of degrees Celsius near the rim to values closer to the background interstellar radiation field deeper inside. These gradients define the initial thermal conditions that collapse will inherit. Cooler gas lowers the gene's mass and favours fragmentation into smaller cores. Warmer gas raises it and favours fewer, larger condensations. The cloud evolves under external pressures from the spiral arm as well. Converging flows along the arm's spine can deliver fresh material into the parent complex, thickening the layer behind the rim and changing the balance between erosion and accumulation. Supernova shocks from earlier generations in the arm can cross the region and momentarily increase pressure-right shells into the molecular gas or stir turbulence that later decays. The present structure near the Eagle Nebula includes arcs and ridges consistent with past pressure events, now partly overrun by the cavity and partly preserved in the cloud's interior. Mass estimates for the parent cloud rely on the brightness of carbon monoxide lines, calibrated against regions where dust emission and extinction provide independent measures. The conversion from brightness to mass carries uncertainties because excitation conditions and abundances vary with environment. Dust-based estimates complement the molecular lines by tracing total column density with less sensitivity to local chemistry. Combined maps show that the mass reservoir far exceeds the mass now present in stars within the cluster, implying that only a small fraction of the cloud has turned into stars to date. Star formation efficiency, the fraction of gas converted to stars before feedback disperses. The cloud depends on how long dense gas can resist erosion, and on how often new dense gas is delivered along filaments during the bright phase of the cavity. Timescales in the parent cloud are long compared with the advance of the shell, but short compared with the lifetime of the spiral arm pattern. The sound crossing time for a dense core is measured in hundreds of thousands of years. The time for a filament to feed material into a clump spans a few million years. The duration over which the cavity maintains strong ultraviolet flux is of similar order. These overlapping times suggest that some cores reach instability and begin collapse while the rim is still advancing, while others remain near equilibrium until external pressure decays. The cloud remains a dynamic balance rather than a static reservoir, with inflows, erosion, and internal reorganization proceeding together. Measurements across wavelengths align with this view. Radio maps of carbon monoxide trace long, cold lanes that curve behind the rim. High-density tracers pick out compact cores embedded along those lanes. Infrared images register warm dust at the rim and cooler dust deeper inside and identify embedded sources where collapse has begun. Extinction maps derived from background star counts outline column density peaks aligned with filaments. Polarization maps show the orientation of magnetic fields with respect to the gas. Each window adds a layer to the three-dimensional picture of the parent cloud. Together they show a cold interior protected by dust, fed by converging flows along the arm threaded by magnetic fields and pressed from one side by the ionized cavity. Within the fixed outer to inner path, this region defines the material context that the boundary shell meets and reshapes. It supplies the dense pockets that either resist and survive to form stars or yield and disperse back into the diffuse medium. It sets the temperature, density, and support that determine whether compression triggers collapse or merely sculpts the surface. It provides the filaments that channel gas toward the rim and the cores that sit in the shadows of denser caps. With the parent molecular cloud now described as a cold, structured reservoir beyond the bright rim, the narrative can step inward again without changing frames, turning to the specific shapes along the interface where these conditions and the advancing front produce the tall dark columns and knots that mark the boundary in the Eagle Nebula. The tall columns at the Eagle Nebula's rim are the shaped remnants of denser material that withstand erosion longer than their surroundings. They stand where the ionized shell meets a clumpy face of the parent cloud. Each column consists of a trunk, a bright curved cap at the sunlit tip, and a tapered tail that projects away from the young cluster. The cap faces the ionizing light. It is a thin, heated skin where atoms are stripped gas warms and a steady stream of material flows off the surface into the cavity. The trunk lies behind the cap. It remains mostly neutral and cold, protected by the mass in front. The tail extends into the shadow where radiation is weaker and where the gas keeps its molecular state over greater depth. This simple geometry repeats along the rim with variations set by local column density field direction and the angle at which light arrives. The scale of the pillars is measured in light years. Individual trunks run for a few light years from their caps toward the deeper cloud. Their width span fractions of a light year to about a light year, narrowing toward the cap, where erosion is most efficient, and thickening into the interior where shielding grows. The cap's radius of curvature matches the balance between external pressure and internal support. Higher pressure produces tighter caps, lower pressure produces broader, flatter caps. Embedded along the first fraction of a light year behind many caps lie knots and globules, with densities higher than the surrounding trunk. Some knots are compact enough that their gravity is important. Others are merely bumps left by earlier shocks. The surface of the trunk shows ripples aligned roughly with the pillar's axis or wrapped around it. These are the imprints of instabilities in the thin compressed layer at the cap, and of small variations in the flow of photo-evaporating gas across the face. The cap is a moving boundary. Ultraviolet photons heat and ionize only a thin depth of the exposed surface at any moment. Gas there expands and streams away at a few kilometers per second, leaving cooler gas behind to replace it. As this replacement proceeds, the cap migrates slowly into the trunk. The rate of retreat depends on the photon flux, the density and the neutral material just under the cap, and the dust content that shares the heat load. Where the flux is strong and the density is modest, the cap thins and the retreat is rapid. Where the flux is filtered by intervening dust, or where the underlying density is high, the retreat slows. At edges where the cap bends around a protrusion, the flow of ionized gas sweeps tangentially and can peel thin sheets from the surface, leaving filigree that points sideways into the cavity. The trunk holds a mix of densities and supports. Deep inside, far from the cap, temperatures remain only a few tens of degrees above absolute zero, and turbulence is modest. Closer to the cap heating, by far ultraviolet light penetrates through small pores and raises the temperature of dust and gas within a thin skin that thickens with distance from the apex. Magnetic fields thread the pillar. Polarization of dust emission indicates that fields run roughly along the long axis in many cases, although in places they bend around dense knots or drape across the surface where curvature is strong. This geometry helps the trunk resist lateral compression and guides gas flows toward the axis. It also helps explain the smoothness of some pillar flanks and the presence of ridges aligned with the field. Shadowing sets the tail. The cap blocks direct ionizing photons over a conical region that opens behind the apex. Inside this shadow, the gas remains molecular over longer paths. Diffuse radiation from the surrounding ionized gas still reaches the tail and maintains a warm, partially dissociated skin on its sides, but the centerline stays cold and dense until other processes disturb it. The tail lengthens as the cap recedes because new material continuously enters the shadow. Over time, gravity and pressure gradients can funnel gas along the axis toward the interior cloud, building up the trunk even as the cap ablates. In other cases, the tail thins as lateral photoevaporation, and shear remove material from its edges faster than inflow can replenish it. Along the pillar sides, small knots cast their own secondary shadows and grow miniature tails. These evaporating gaseous globules sit on or near the surface, where curvature in the cap focuses compression. Each globule develops a bright rim on the sunward side and a dark tapered wake behind it. The smallest globules shrink quickly and vanish. Larger ones persist and can decouple from the pillar face as erosion carves around them, leaving them behind as isolated teardrop shapes drifting slowly relative to the flow. In a few cases, compact globules harbour dense cores with rising central pressures. Those cores are shielded enough to begin collapse, while their outer layers continue to evaporate, showing both inward motion and outward flow at once. The pillar surface is a record of repeated slow shocks. The pressure of the ionized shell launches a compression into the neutral skin beneath the cap. The compression collects gas into a thin layer that cools rapidly. Curvature and gravity cause the layer to wrinkle. Inward dents focus pressure and deepen, raising density locally. Outward bulges feel less push and lag. With time, the wrinkled skin breaks into arcs and beads. Some beads slide along the surface under shear from the evaporating outflow and merge with others downstream. The overall effect is a textured face with bright knots on the rim and drape streaks pointing away, all moving slowly as the cap advances. Measurements of motion and density across the pillars come from line profiles in the optical and the radio, and from infrared emission of warm dust. Ionized gas at the cap shows line widths and small Doppler shifts consistent with outflow speeds of a few kilometers per second. Just behind molecular lines reveal narrower widths, where turbulence has decayed in the shadow. At yet greater depth, the spectra broaden again, where flows along filaments feed the pillar base. Brightness ratios of lines from sulfur and oxygen mark higher densities at knots and lower densities along smoother segments. Maps of dust temperature show warm rims that cool by a few tens of degrees Celsius between the face and the interior within less than a tenth of a light year. The pillar bases connect to the larger cloud through filaments that run into the arm. These roots supply mass to the trunk and set how long the column persists. Where roots are strong and well shielded, inflow along the filament can maintain the pillar's central density against ablation at the cap. Where roots are thin or disrupted by older shells, the pillar tapers and eventually detaches, leaving behind a trail of globules that shrink and fade. The lifetime of a pillar as a distinct structure is measured in a few 100,000 to a few million years, comparable to the bright phase of the cavity, but shorter than the orbit time of the arm segment. As a result, the ensemble of pillars along the rim changes on the same timescale as the cluster's hottest stars evolve. Not all columns are straight. Some bend in gentle arcs that reflect lateral pressure gradients along the rim or the push of oblique shocks that crossed the face before the cavity formed. Others twist where small differences in ablation rate along the sides rotate the axis slowly. These shapes are not decorative. They encode the direction of external flows and the pattern of earlier compression. Where two nearby caps face slightly different angles to the radiation field, the spaces between their trunks are eroded more quickly, cut in channels and leaving isolated spires. Where three or more protrusions crowd the outermost erodes fastest, and the innermost survives longest, producing layered stacks of columns that sit one behind another when projected on the sky. Inside, several caps lie compact high column density regions that resist both photoevaporation and immediate collapse. They are near hydrostatic balance supported by thermal pressure, residual turbulence and magnetic tension. Compression from the cap may push them across the threshold for instability if it persists. If compression relaxes or shear strips mass from their surfaces faster than gravity can gather it, they stabilize and thin. The outcome hinges on sizes measured in tenths of a light year and on column densities measured in tens to hundreds of solar masses per square parsec, written here without symbols. In the Eagle Nebula, both outcomes are present along different segments. Some cap cores show signs of inward motion and rising central temperature. Others show smooth thinning rims and no dense interior. The interaction between cap erosion and interior flows sets a slow mass budget. Photoevaporation removes gas from the exposed face and delivers it to the cavity. Inflow along the pillar base and sides adds gas from the parent cloud. If inflow matches loss, the trunk maintains its width while the cap retreats. If loss exceeds inflow, the trunk narrows with time. Observations that compare silhouettes in visible light with thermal dust, emission in the infrared, and with molecular column density maps suggest that some Eagle pillars are currently near balance while others are in decline. Balance appears where roots are thick and where the field guides gas along the axis. Decline appears where roots are cut by gaps in the cloud or where field orientations channel gas away. The fine skin that separates ionized and neutral material carries its own internal chemistry and grain physics. Ultraviolet light changes the charge on dust grains, alters their ability to stick or to repel, and can break apart complex molecules attached to their surfaces. As grains charge and discharge, they couple more or less strongly to the gas, changing how momentum is shared across the boundary. In microphysical terms, these effects change the thickness of the layer and the rate at which energy is exchanged. In structural terms, they tune the sharpness of the bright rim and the transparency of the skin to different wavelengths. The result is that the same boundary looks sharp and bright in visible lines, softly glowing in certain infrared bands, and nearly invisible in some radio tracers that see only deeper, colder gas. Evidence of internal alignment within the trunks appears in the distribution of embedded knots that prefer the central axis over the flanks. This alignment indicates that gravity and pressure gradients direct gas toward the axis faster than lateral ablation can remove it at least over part of the pillar's length. It also suggests that if collapse occurs inside a trunk, the earlier sites will lie near the axis a short distance behind the cap, where compression is strongest and where shielding remains high. In places where no interior cores are present, the same alignment simply records focused flow without collapse. The pillars live at the interface where the conditions of the spiral arm, the pressure of the cavity, and the structure of the parent cloud meet. Their heights and widths follow from the competition between internal support and external ablation. Their caps are the moving loci where radiation and pressure consume the surface. Their trunks are the protected channels that feed the interior. Their tails are the shadows that lengthen as the cap retreats. In a wide view, they are markers of the shape of the buried ridge. In a narrow view, they are laboratories for the physics of fronts, shocks cooling layers, and magnetized flows at interstellar pressures. Keeping the frame steady, the description remains at the boundary while moving one step further inward to the kinematics and microphysics of the ionization front itself. There, the advance of the bright rim across the pillar faced the coupling between shocks and evaporation, and the transfer of momentum and heat across the thin skin set how fast the cap retreats and how the underlying trunk responds without leaving the scale of the interface that defines these columns. At the very surface, where bright nebula light meets the darker pillar, the ionization front advances as a thin active skin. On the starward side, hydrogen atoms lose electrons and the gas warms quickly. Just behind that layer, the ionized flow accelerates away from the surface as a steady breeze. On the pillar side of the skin, molecules break apart in a narrow band, and then give way to colder, denser gas that remains largely neutral. The front is thin in distance, yet rich in processes. It regulates how momentum and heat pass from the cavity into the pillar. It sets the rate at which material is peeled from the surface, and it decides whether the layer just beneath is gently compressed or sharply shocked. The advance does not happen at the same pace everywhere. It speeds up across soft, low-density patches and slows to a crawl against deeper clumps, turning a smooth boundary into a textured map of resistance and retreat. Two modes of propagation help describe the front. When a young cavity first lights ionizing photons can outrun motion and create a large volume of ionized gas before pressure has time to respond. In this early mode, radiation drives the expansion by filling space with warm electrons and protons faster than the gas can move. As the cavity matures, recombinations within the ionized zone require a steady supply of photons just to maintain the state, and pressure from the warm gas takes the lead in pushing the front. In this later mode, a compression wave travels into the neutral side and often steepens into a shock. The shock raises density in a thin slab that hugs the front. Cooling in the slab is efficient. The slab collapses into a thinner, denser sheet that grows heavy enough to wrinkle under its own weight, and under gradients in the push from behind. In pillars that face the cluster squarely, this sheet folds into beads and arcs along the rim. In pillars that face at an angle, the sheet is sheared by glancing outflows from the cavity, and sheds ribbons that drift down the sides. Photoevaporation is the quiet engine that removes mass. Ultraviolet light heats the illuminated skin to a temperature at which the sound speed is of order, a few kilometers per second. Gas at that speed expands away from the surface streams into the cavity, and leaves cooler gas to take its place. The mass flux off a unit area depends on the photon rate that reaches the skin and on the density just beneath. Dust both absorbs and scatters the incoming light, so the microscopic mix of grains helps set the skin's temperature and thickness. Where dust is plentiful and grains are small, heating spreads through a slightly wider layer, and the peak temperature is lower. Where dust has been partly cleared by earlier flows, the heating is more concentrated and the layer thins. In both cases, the outflow establishes a gentle pressure gradient that leans on the neutral gas and helps guide the slow shock that follows. The structure across the front can be read in emission. In visible light, bright lines from hydrogen and oxygen trace the ionized side. Just inside the pillar, infrared lines from carbon and oxygen in low ionization states mark the transition band. Farther in, rotational lines from common molecules announce the return of the cold interior. Ratios of selected lines respond to electron temperature and electron density, and to the rate at which atoms collide and cool. Maps of those ratios across a pillar face show smooth gradients where the layer advances evenly, and sharp steps where the layer meets an obstacle and is forced to bend. The steps tend to sit above density peaks that also appear in molecular traces tying the radiative picture to the mass distribution beneath. Shocks just inside the front are slow and radiative. They travel through gas that is cold and nearly molecular, and that cools rapidly when compressed. The strong push briefly raises temperature, but the gas then radiates the heat away and collapses into a denser state. Because cooling is fast, the shock leaves no broad plateau of warm subsonic flow. Instead, it writes a thin, compressed line into the pillar. The line is not straight. Curvature of the surface focuses the push into pockets and eases it around protrusions, so the compression tapers into cup-shaped arcs around knots and stretches into long ridges along flanks. Over time, the ridges collect enough mass that gravity begins to help. Where that happens, the ridges sag into the pillar or seed elongated cores just behind the cap. Momentum transfer across the skin is a blend of radiation forces and gas pressure. Photons carry a small but steady push that is shared with the gas through dust. Gas pressure contributes a larger push and is carried into the pillar by the shock. Magnetic fields add tension that resists sideways motion and channels the compressed flow along the pillar's length. The balance among these agents varies with location. Near the cap apex, where the incoming flux is highest, and the curvature is tight, radiation and pressure align and drive a compact, nearly axisymmetric layer. Along the shoulders, where the surface tilts away, diffuse radiation dominates, and the evaporative flow glances across the face, sculpting lace, like sheets that peel from the rim. Instabilities born in the thin layer can grow under these conditions. If a ripple presents a slightly denser crest to the incoming push, the crest slows and gathers more gas, while the trough receives a weaker push and lags, deepening the pattern. If the layer is curved, gravity enhances sagging at crests and aids separation of arcs from the face. Shear from the evaporative wind stretches small features downstream. Magnetic tension partly stabilizes short ripples parallel to the field but allows longer modes to grow. The combined action explains the observed mix of smooth sections and beaded chains. It also explains why beading prefers some orientations over others, and why filigree often trails away from knots in consistent directions. Kinematics on the ionized side record the outcome. Spectral lines from the cap show split or skewed profiles where the outflow bends around the surface. The blue side of a line can carry extra weight along sight lines, where the flow comes toward the observer, and the red side can carry extra weight where the flow departs. Across the apex, the line narrows and centers as the flow becomes more symmetric. A map of such profiles yields a simple picture, a cap that breathes a steady breeze into the cavity stronger, where light falls most directly weaker, where the front is shaded by nearby structures. On the neutral side, lines from molecules narrow and shift by small amounts that mark the slow advance of the compression deeper into the trunk. Heat flows across the skin both by radiation and by microscopic contact between hot and cold gas. Thermal conduction tends to even temperature gradients in very thin regions, but magnetic fields reduce conduction across the field and allow sharper transitions to survive. Small-scale mixing layers can also arise where the evaporative flow scrapes the surface and lifts wisps of neutral gas into the ionized side. Those wisps are heated, torn apart, and blended into the breeze. Their destruction adds cooling lines to the cap's spectrum and leaves faint feathery streaks that align with the direction of flow. Over time, repeated mixing keeps the ionized layer supplied with freshly ablated atoms, while also chipping at the surface under the rim of the cap. The retreat speed of the front into the pillar depends on the ratio of the incoming photon rate to the column density of gas along the local normal to the surface. High column density gives more recombinations per unit area and slows the advance. Low column density gives fewer and speeds it. Because column density varies across the face, the cap retreats unevenly and tilts. The tilt sets the sense in which the tail lengthens and the side on which filigree is shed. It also decides which embedded knots remain buried and which are uncovered and exposed. Once uncovered, a knot grows its own rim and its own evaporation flow, and the front must root around it. This routing pushes extra pressure into the sides of the knot and can in larger cases trigger collapse inside while the outside continues to erode. Observations that span many years catch small but real changes. High-resolution images taken at different epochs show that some edges shift by distances that, when divided by the time between images, translate into speeds of order, a kilometre per second, in line with the physics of photoevaporative flows and slow shocks. Small arcs drift, thin strands detach, and the sharp outline of a cap softens or tightens depending on local pressure. These subtle motions support the picture of a living boundary rather than a static edge, and provide an independent way to test models that couple radiation gas dynamics, cooling, and dust physics. The front also regulates the supply of ionized gas to the wider cavity. The evaporative breeze from many square light years of rim adds mass to the interior that later cools or is carried away through open channels. Where the cavity vents into lower density surroundings, a pressure gradient accelerates the ionized gas outward in a gentle layered flow. The total mass loss from a pillar is then a balance between what the cap sheds and what the roots supply from the parent cloud. The front is thus not just a local skin. It is a junction that couples the cold reservoir to the warm interior and that controls the exchange between them. Inside the pillar, the compression that the front delivers tunes the initial state for any dense cores that form. Modest sustained pressure raises density while preserving low temperature, a combination that moves a core toward collapse. Impulsive short-lived pushes can stir turbulence and delay collapse. The microphysics of the front decides which regime applies at a given spot. Where the cap is smooth and the evaporative flow is steady, the push is gentle and long. Where the cap is wrinkled by instabilities and fattened by recent shocks, the push arrives in pulses. In this way, the fine structure of the front influences the pace at which the interior assembles stars. Across all of these details, the scale remains small compared with the size of the cavity, yet large compared with a single star's disk. The front is a few thousandths to a few hundredths of a light-year thick, depending on local density and field geometry. The shock-compressed slab beneath it is thinner still. These thin layers write the visible lines that outline the pillars and that give the nebula its crisp edges. Their behaviour is set by the same conditions that govern the whole region: the photon budget of the cluster, the ambient pressure along the spiral arm, the clumpiness and magnetization of the parent cloud, and the time since the cavity began to expand. With the moving boundary now resolved to the scale of its skin, the next inward step keeps the frame fixed, and follows material just behind the front into the densest clumps and globules that it confronts. There, gravity contends with the external push, and the earlier stages of starbirth begin inside shielded cores, even as the same cores lose mass from their exposed faces, a narrow theatre in which both assembly and erosion proceed at once. Just behind the moving rim, where light weakens and pressure still runs high, small islands of gas and dust persist as dense clumps and globules. Many sit on or near pillar caps as rounded protrusions whose sunlit faces glow and whose interiors stay cold. Others lie a short distance inside the shadow, detached from any obvious surface but still close enough to feel the external push. The smallest of these bodies are evaporating gaseous globules, compact knots with bright rims on the starward side and tapered wakes behind them. The larger ones are embryonic cores with masses and sizes great enough that their own gravity matters. Every example occupies a narrow band of conditions, enough shielding to keep molecules intact and temperatures low enough external pressure to raise density and sharpen gradients, and enough time without disruptive shocks for internal motions to settle. The physical state of a dense core is simple to state and slow to arrange. Temperatures fall to roughly 10 to 20 Kelvin set by molecular line cooling and by faint dust emission into space. Number densities rise by orders of magnitude above the surrounding cloud so that collisions become frequent, and the gas behaves like a smooth medium rather than as separate particles. Turbulence left from earlier assembly decays, leaving only subsonic motions or quiet rotation. Magnetic fields thread the core and provide part of its support, but collisions between neutral molecules and the much rarer ions allow the neutrals to drift slowly with respect to the field, a transport that over long spans lets gravity collect mass toward the centre. When the mass inside a given radius exceeds what thermal pressure and magnetic tension can bear, the core crosses the threshold from near balance into slow inward motion. External compression pushes cores toward that threshold. The advancing ionization front delivers a raised pressure into the photodissociation skin and into the first molecular layers beneath. Where a compact clump lies, this pressure stratifies the surface into a thin, dense layer that transmits the push inward as a radiative shock. Because the gas cools rapidly, the shock leaves behind a denser state at almost the same low temperature. The result is an increase in central concentration, without a matching rise in thermal speed which moves the core closer to instability. If the push endures for a long fraction of a million years, the effect is cumulative. If it arrives in pulses separated by long lulls, the core may re-expand between pulses, delaying collapse. Photoevaporation tries to do the opposite. The illuminated face of any exposed core sheds gas at a rate set by the local photon flux and the binding of the outer layers. Mass loss removes part of the very material that gravity would use to deepen the potential well. Whether loss or gain wins depends on the core's column density and on the direction of inflow along surrounding filaments. Core heads deeply buried behind thick caps receive enough compression and enough fresh mass from the flanks to grow despite evaporation from the tip. Shallow caps with thin roots lose mass faster than inflow can replenish it, and the internal density peak never gathers. This competition explains the mixed scenes seen along a single rim. Some globules shrink and fade. Others inside similar bright rims shelter cores that are getting denser with time. Clues that a core has begun to collapse appear before any star lights its interior. Molecular lines from heavier species with narrow thermal widths show a subtle asymmetry across the face. The near side of the core absorbs a small part of the line, emitted from deeper layers, leaving a skew in which the brighter peak lies at a slightly higher speed than the absorbed dip. The skew signals inward motion of the cold, front half of the core against the warmer interior. Dust emission strengthens at the centre relative to the outskirts as column density increases. At the same time, the bright ionized rim moves slowly across the face, without breaking into the interior, a sign that the mass loading at the front exceeds the ablation rate. Where such conditions persist, the system approaches the stage of a true protostar forming inside an envelope. Rotation and magnetic geometry set how the collapse proceeds. Even a slow initial spin is amplified as material falls inward and conserves angular momentum. Magnetic fields tend to align rotation axes with filament directions, or with a pillar's length. If ambipolar drift has bled enough magnetic support from the inner mass, The center contracts and flattens into a small dense object surrounded by an infalling envelope whose angular momentum soon demands a disk. If the field remains, strong contraction is slower and proceeds along the field lines, shaping an elongated inner region that later rounds out as support weakens. In either case, the earliest inward motion gathers gas over tens of thousands of astronomical units, while the outer layers remain almost unchanged, a geometry consistent with the presence of a bright rim and a cold tail around a dark center. Chemistry records both shielding and the age of contraction. In very cold, dense zones, common molecules freeze onto dust grains, lowering their gas phase abundances and changing which lines remain bright. Less volatile species become traces of the coldest interior. Deuterated molecules grow more abundant where temperatures are low enough that fractionation favors heavy hydrogen in reactions. As the center compresses, weak internal heating from compression and from the first release of gravitational energy begins to sublimate the most volatile ices, changing the chemistry in a small central patch without yet producing visible light. Farther out, the surface of the core keeps its warm photodissociated skin maintaining a gradient from ionized to atomic to molecular species over a distance of only a few hundredths of a light year. Globules that are not yet true cores still show organized behavior. Their rims thicken under repeated slow shocks. Their wakes align and thin under shear from the evaporative flow. Their interiors remain isothermal and near balance, with support shared among thermal pressure, residual turbulence, and magnetic tension. Some detach from the pillar face as erosion cuts channels around their flanks, leaving them adrift in the cavity with a sunward bright rim and a trailing shadow. Detached bodies evaporate faster because supply from the parent cloud is cut. Yet if their initial column density is high, they can still carry a dense interior long enough to begin collapse, while shrinking from the outside. Gravity pressure and radiation meet again in the question of how many stars a single pillar rim can host. Where the rim is smooth and the front advances evenly, compression is uniform, and the number of core seeds remains small. Where the rim is wrinkled and beaded by thin layer instabilities, many small pockets reach high density and can host several small cores in a chain. The field often aligns these chains with a pillar axis, a pattern seen in polarization maps of dust emission, and in the distribution of embedded sources in infrared images. Chains near the cap are more likely to be exposed early and to lose mass from their tips. Chains deeper inside remain protected longer and are more likely to complete collapse. Timescales in this zone are stepped. The front advances across a pillar face over hundreds of thousands of years. A core that has just crossed the stability threshold contracts slowly at first on a similar timescale, and then accelerates as central density rises. The stage before any central object forms occupies a long fraction of a million years. Once a hydrostatic center appears, the assembly of a protostar continues with growing luminosity and with the rise of a disk and outflow. All of this occurs while the external rim keeps moving. As a result, the same pillar can host cores at different stages, separated by less than a light year, one just beginning inward motion, behind a thick cap, one already warming a small zone deeper inside and one still in balance near the shadowed tail. Evidence for cores at these stages in the Eagle Nebula's columns includes cold dust peaks that sit a short distance behind caps, high-density molecular tracers concentrated at those peaks, and young stellar objects detected in the infrared, whose light is reddened by thick envelopes. The youngest objects appear as faint, broad infrared sources with no optical counterpart, and with spectral energy distributions that rise at long wavelengths. Slightly older ones show compact mid-infrared emission, and in a few cases faint jets that begin to appear against the dark background. Cores without internal sources are identified by their narrow self-absorbed lines, and by the absence of any warm knot at the center of their dust emission. Together, these indicators map a progression from compressed but starless clumps to very young protostars hidden inside the same pillars that are evaporating at their faces. Collapse remains uncertain in the smallest, most exposed knots. There, the external push is strong, but the reservoir is small, and evaporation removes mass from the exact place where a central concentration would form. Some knots thicken briefly under a passing compression, and then thin again as the front moves on, leaving no remnant. Others accumulate mass from the sides, faster than the tip can shed it, and cross the threshold quietly. The deciding factors include the alignment of filaments that feed the knot the angle of the front, the local field geometry, and the recent history of shocks that either stirred or calmed internal motions. Because these vary along the rim, outcomes differ pillar to pillar and even along a single face. Across the ensemble of globules and cores, one property is constant. The region remains embedded within the same spiral arm environment and within the same cavity that provides both pressure and light. No core forms in isolation. Each sits in a field that sets its boundary conditions and in a hierarchy that feeds it from larger scales. The cold, dense interior responds to the slowest, most persistent part of that field and filters out the faster, noisier variations. In this way, the inner assembly of a core remembers the average push of the front and the steady inflow along the pillar base more than any single ripple on the rim. The step inward now leads from starless cores to the first objects that light from within. In these, gravity has already made a central well that begins to heat by compression. Material falls through an envelope, and because of conserved angular momentum settles into a small disk before reaching the center. The next region therefore keeps the same frame and follows how a protostar gathers mass from its envelope, while the same envelope loses mass from its sunlit face, an evolution in which accretion and evaporation proceed together within the protected axis of a pillar and under the same external field that shapes the rim. Inside a dense core that has crossed the threshold into inward motion, gravity funnels gas toward the center and builds the first hydrostatic object. The interior warms by compression, but remains buried under an envelope that is still cold and opaque. Material does not fall straight in. Even a small initial spin grows as the radius shrinks so angular, momentum diverts the flow into a flattened structure around the new center. A disk appears on scales of a few tens to a few hundreds of astronomical units, thin compared with the envelope and aligned more often than not with the pillar's long axis or with the filaments that feed it. Gas spirals inward through the disk under the combined action of gravitational torques, magnetic stresses and turbulence stirred by the infall itself. The young object at the middle gains mass in steps, brightening first in the far infrared, where the envelope re-radiates the heat, and only much later at shorter wavelengths when the envelope thins. The envelope continues to feel the external field. The bright rim crawls across its sunlit face, and a slow evaporative breeze carries atoms and small grains away toward the cavity. At the same time, the opposite side of the envelope draws supply from the pillar's root along the protected axis. This asymmetric setting gives the forming system a head and a tail. The head loses mass from one side under ultraviolet light, and gains mass from the other under gravity. The tail feeds the midplane where the disk spreads outward as it accepts new material. The competition between gain and loss sets how quickly the central object grows and how long the envelope lasts. Observations of similar objects in bright-rimmed pillars show that accretion can persist, even while the illuminated face thins, provided the protected side remains connected to a dense filament. As accretion proceeds, a second phenomenon rises. A narrow, fast wind emerges along the rotation axis, launching from the inner disk and from the magnetic interface between disk and star. This outflow clears cavities through the envelope and appears on larger scales as bipolar jets, straight or slightly wiggled beams of shocked gas that run for a fraction of a light year into the surrounding pillar shadow. The jet carries away angular momentum and allows gas in the disk to fall inward more readily. Where the jet strikes denser pockets, it lights knots of emission that move slowly outward when viewed over years. These knots mark places where the flow encounters clumps, or where the ejection engine pulses. In the Eagle Nebula, faint signs of such jets appear in narrow lines that trace shocked molecules and in dim optical filaments seen against the dark background between columns. The disk itself is not a static ring. It spreads under internal stresses, drawing gas inward and pushing some outward. Spiral features can grow in the disk where the mass is high and the cooling is efficient, transporting angular momentum through gravitational torques. Magnetic fields thread the surface and couple to the ionized fraction of the gas, driving a slow wind that peels mass from the top and bottom layers and adds to the bipolar flow. Turbulence stirred by infall and by instabilities mixes material radially and vertically, moving heat and dust grains and setting the conditions for later solid growth once the envelope thins. In this earliest phase, the disk remains deeply embedded and is seen mostly through its effect on the spectrum of the envelope and through the silhouette it casts at mid-infrared wavelengths where the background nebula glows. Accretion is unsteady. The young object gains most of its mass in episodes when the inner disk dumps material onto the centre faster than average. These bursts heat the inner regions and push small cavities into the envelope along the poles. Between bursts, the disk refills from larger radii and from the envelope. The cause of the burst can be the inward march of a dense ring, a gravitational instability that drives mass toward the centre, or a change in the magnetic connection that regulates how the inner edge of the disk hands material to the star. In the bright rim environment of the pillars, external pressure fluctuations can also modulate the delivery of gas at the outer edge, adding to the irregular rhythm. Radiation from the young object and heat from shocks along the jets begin to change the chemistry of the nearer surroundings. Ices in the inner envelope sublimate and release molecules that were trapped on dust grains when the gas was cold. The disk surface glows in lines that require warm temperatures and traces the start of a layered structure in which a cold interior is capped by warmer, partially ionized skin. Dust grains grow as they collide and stick first into fluffy aggregates and later into compact pebbles as turbulence and gas drag stir and settle them. These changes are still hidden behind the envelope, but their imprint appears in the spectral shape of the re-radiated light and in faint absorption features that mark specific ices along the line of sight. Meanwhile, the illuminated face of the envelope continues to erode. Photoevaporation picks up where the jet cavities approach the surface, creating small windows through which radiation from the young object leaks into the pillar shadow. These windows expand slowly and their edges show curved rims that resemble miniature versions of the larger pillar caps. If the external ultraviolet field strengthens either because the cap retreats or because a path opens through the cavity, the illuminated face can thin faster than the protected side can supply mass. In such cases, the envelope peels back until only the disk remains thick, and the young object emerges as a compact infrared source with a narrow dark lane across a small bright nebula shaped by its own outflow. The direction and collimation of the jet record the inner geometry. Jets tend to align with the local magnetic field on scales of the core and the pillar, but they also precess slightly if the disk wobbles under the pull of infalling clumps, or if the central object is not alone. Slight bends in the shocked filaments and chains of knots that trace shallow arcs give away such motions. The degree of collimation varies with how well the magnetic surfaces in the inner disk can guide the wind. Strong-ordered fields yield narrow beams. Weaker or tangled fields spread the flow into wider cones. In the Eagle, nebula's setting, where the external field shows an ordered component along many pillars, a preference for aligned jets is plausible, though the evidence remains limited by the depth of the embedding and by the foreground glow. Accretion and feedback compete on small scales, just as erosion and inflow compete on large scales. The outflow clears cavities that reduce drag on infalling gas along the poles, but can also vent the inner pressure that would otherwise help compress nearby clumps. Shocked shells along the cavity walls can trigger small condensations where they run into dense pockets, while at the same time the removal of mass from the central zone reduces the supply to the upper layers of the disk. The net effect is a delicate balance in which the young system regulates its own growth and nudges its neighbourhood without dominating it. In a pillar with several embedded objects, the cavities can overlap and rearrange flows, producing a web of channels that join the larger shadow with the ambient cavity. Timescales step down again at this stage. The free fall time at the densities of the inner envelope is measured in only tens of thousands of years. The time for a jet to traverse a fraction of a light year is of the same order. The disk evolves more slowly over hundreds of thousands of years as it processes the mass delivered by the envelope. The envelope itself lasts as long as accretion exceeds erosion on the illuminated face, and as long as supply continues from the pillar's root. Because the external rim keeps advancing, an embedded protostar can spend its first 100,000 years under a cap that gradually recedes, then emerge into a small personal cavity, while the larger pillar continues to thin. Observations across wavelengths confirm each element of this picture in related regions and where sensitivity permits in the Eagle Nebula. Cold dust peaks behind caps stand where cores are thickest. Faint narrow jets appear in emission from shocked molecules within pillar shadows. Mid-infrared images show small reflection cavities around compact sources and dark lanes that betray disks seen edge-on. Radio lines reveal infall signatures in cores, and gentle outflows along axes aligned with elongations in the dust emission. These signatures are subtle because the background is bright and the pillars are crowded, but together they reveal that even under external erosion, the protected axes of columns can host the same early accretion physics seen in quieter clouds. As the envelope thins further and the disk takes over as the main reservoir, the system will move to a stage where direct starlight escapes along polar cavities, while the mid-plane remains opaque. The outflow will widen its opening angles and carve a more pronounced hourglass through the remaining envelope. The disk will cool toward its mid-plane and begin to decouple the motions of solids from gas on small scales. Those later steps remain inside the pillar shadow for a time and remain subject to the external field that continues to peel at the sunlit face. The current focus holds on the first assembly, where mass still arrives primarily from the envelope, and where the outflow is the first sign that the inner engine is at work. Keeping to the established frame, the description has followed material from a compressed core to a young source with a disk and a jet, all within the protected interior of a pillar, and under the same external pressure that sculpts the rim. The next inward step stays at the same location, and narrows to the disk itself, where gas spirals through a thin rotating layer, where grains grow and settle, and where the outflow is launched from the inner regions, while the illuminated face of the surrounding envelope continues to evaporate into the cavity beyond. The disk forms as a thin rotating layer wherein falling gas meets the barrier of angular momentum. It spreads around the young object with a radius of a few tens to a few hundreds of astronomical units, and settles toward a vertical structure set by the balance between the pull of gravity downward and the push of gas pressure upward. Temperatures fall from warm inner zones to cold outer zones, and densities rise sharply toward the midplane. Rotation is nearly Keplerian, meaning that orbital speed decreases with distance in a way set by the central mass. Small departures from this rotation carry the stresses that move matter through the disk. Those stresses come from magnetic fields, threading the gas from spiral patterns that arise when the disk is heavy enough to feel its own gravity, and from turbulence that stirs layers where the ionized fraction allows gas to couple to fields. Accretion proceeds when angular momentum shifts outward and mass shifts inward. Near the surface, ultraviolet light from the cluster and X-rays from the young object ionize a small fraction of the gas enough that magnetic stresses can link neighbouring rings of material. These stresses exchange momentum and let gas drift deeper toward the star. In the interior, where ionization is weaker, currents still thread the gas along field lines that pass through the disk and out into the surrounding envelope. The fields launch a slow wind that rises from the upper layers and carries angular momentum away along open lines. This magnetized wind complements the narrower, faster jet from the very inner region. Together, they ease the inward journey of gas through the disk while allowing the disk to remain relatively cool and thin. Spiral features grow where the disk is massive with respect to the young star and where cooling is efficient. The spirals act as a conveyor, moving angular momentum outward through gravitational torques and drawing gas inward along their crests. The pattern does not remain fixed. It appears and fades as the disk mass and temperature change with time, and as new material falls in from the envelope in clumps. Clumps that arrive with different angles of approach can tilt the outer disk slightly or thicken it locally, producing warps that precess slowly. These warps can alter how the inner jet points and can shade parts of the envelope, adding asymmetries to the reflection cavities seen at mid-infrared wavelengths. Dust mixed with the gas starts as grains brought in from the molecular cloud. Collisions make grains stick and grow from submicron sizes into aggregates that measure many microns and then into millimeter and centimeter pebbles, where densities and relative speeds permit. Growth proceeds fastest near the midplane, where gas is densest, and relative motions are gentle. The grains interact with the gas through drag. Large grains feel headwinds because the gas orbits slightly slower than a pure Keplerian speed due to its internal pressure. The headwind causes grains to lose angular momentum and drift inward. Small grains remain more tightly tied to the gas and move slowly. Vertical settling occurs at the same time. Grains sink toward the midplane under gravity while turbulence mixes them upward. The outcome is a layered dust distribution that thickens towards small sizes and thins toward large sizes. Radiation from the young object warms the inner disk and creates a radial temperature gradient. The inner rim where dust begins to sublimate sits at a small radius, where temperatures reach many hundreds to a few thousands of degrees Celsius depending on composition. Beyond that rim, the surface layers absorb light and re-radiate it in the infrared. The midplane remains cooler and is heated mostly by the reprocessed light from above and by viscous dissipation from the slow inward drift. This thermal structure sets where certain molecules remain in the gas and where they freeze out onto grains. Freeze-out boundaries or snow lines in common usage mark radii where water, carbon monoxide and other volatiles switch between solid and gas. In bright-rimmed pillars, these boundaries can shift as external ultraviolet light warms the disk surface more strongly than in quieter clouds while the midplane stays cold. The inner region where the jet launches is a narrow zone close to the star where the magnetic field and the rotation combine to fling gas away along the axis. Field lines anchored in the disk act like channels that lead gas upward, while lines connected to the star add a second path that can modulate the speed and collimation. The jet emerges supersonic and plows into the envelope cavities carved earlier, producing bow shocks where it meets denser patches. In the protected shadow of a pillar, these shocks excite molecular lines and faint optical lines. Their knots move slowly outward on human timescales, offering a ruler to gauge the pace of the engine inside. On larger radii, a broader magnetized wind escapes from the disk surface. The wind is slower than the jet and carries less momentum per unit area, but it covers far more of the disk and extracts most of the angular momentum needed to keep accretion going. Gas in the wind is only partly ionized and follows the field out of the gravitational well before expanding into the pillar shadow. As it expands, it interacts with the photo-evaporative stream from the envelope's sunlit face, and with the diffuse ionized gas in the cavity. The interfaces between these flows become sites of mixing and emission, adding faint halos around the jet axis and soft arcs along the cavity walls. The rate at which mass moves through the disk varies over time. When material from the envelope arrives faster than the disk can process it, gas piles up at a few tens of astronomical units and cools. The local surface density increases until gravitational spirals appear and carry the extra mass inward in a short episode. The central luminosity rises for a time and then subsides as the inner disk drains. Such bursts can heat the inner few astronomical units, enough to reset the chemistry and to anneal dust grains, changing their structure from amorphous to more ordered forms. In the environment of the Eagle, Nebula bursts also brighten the small reflection cavities, briefly increasing their contrast against the background glow before fading again. External ultraviolet radiation reaches the disk surface through openings in the envelope and raises a slow, photo-evaporative flow from the outer layers. This flow lifts gas from the disk and reduces the reservoir available for accretion. The rate depends on how large an area of the disk is exposed, on the intensity of the radiation field from the cluster, and on the shielding provided by the pillar. When the cap retreats and opens, new lines of sight exposure grows, and the disk surface loses more mass. When shadows deepen, or when the outer envelope remains thick, the disk survives longer, and can continue to feed the young object even as the illuminated face of the envelope thins. Magnetic geometry aligns the system with the larger environment. Fields in the pillar often run along the axis, and the disk's rotation axis tends to line up with this direction, because collapse proceeds more easily along field lines. Alignment is not perfect. Infall from off-axis filaments and local turbulence can tilt the outer disk by small angles. The inner disk can then precess slowly as it exchanges angular momentum with the outer parts, and the jet can trace a gentle corkscrew through the cavity. Such motions imprint shallow bends on the shocked filaments and vary the brightness of knots as the beam alternately strikes denser or thinner patches. Chemistry in the disk records both the shielded cold interior and the irradiated surface. In the surface, far ultraviolet light maintains a layer rich in radicals and simple ions that emit in infrared lines. In the interior, molecules freeze onto grains, and the gas phase becomes poor in volatiles. Occasional upwelling from turbulence dredges enriched gas into the surface and mixes processed grains downward. Where the disk passes through a burst of accretion heating, desorbs species near the centre, and changes the abundance pattern out to the radius where the additional heat can reach. These signatures are faint in the Eagle Nebula's pillars, but are consistent with patterns seen in similar regions where the background is quieter. The disk remains geometrically thin. Its vertical scale height grows with distance as temperature falls more slowly than orbital speed. This flaring exposes more surface area to external light at large radii and enhances photoevaporation there. It also increases the fraction of external radiation that the disk intercepts, warming the surface and raising the ionization fraction that allows magnetic stresses to operate. The midplane continues to cool and accumulate large grains, building a plane of high opacity that casts narrow, dark lanes in scattered light images when the system is viewed edge-on against the glowing nebula. Within the pillar, several such systems can coexist within a light-year each at a different stage of envelope loss and disk evolution. Their outflows carve overlapping cavities, and their winds blend, but the protected axis and the common external pressure keep their disks thin, and their jets mostly aligned along the pillar length. This shared environment also synchronizes aspects of their evolution. As the cap recedes and exposure grows, multiple disks in the same pillar can begin to photoevaporate more rapidly within a similar span of time, thinning their outer zones, while the inner zones continue to accrete. The small-scale transport of heat and momentum in the disk ties the whole picture back to the larger nebula. Viscous dissipation generated by stresses releases energy that leaves the disk mostly in the infrared, adding a faint contribution to the pillar's shadow. The magnetized wind and jet carry momentum into the cavity, where it helps sustain the ambient pressure that the cavity returns to the rim. In this closed loop, energy from the young object supports a portion of the pressure that shapes the environment that feeds it. The loop remains weak compared with the cluster's broader radiation, and wins but is detectable as local brightening and as narrow features in line maps. Timescales for disk evolution span hundreds of thousands of years. In that period, the envelope decays from the outside under external light, and from the inside under outflows, the disk processes the reservoir that remains, and the jet weakens as accretion slows. In a pillar, the same period witnesses the retreat of the cap by a distance measured in fractions of a light year and the thinning of the trunk under lateral ablation. Some systems will emerge into small isolated cavities while the pillar still stands. Others will remain embedded until the pillar itself erodes into a chain of detached globules. The description remains inside the same frame. It keeps the young system within the pillar shadow, links its accretion and outflow to the local magnetic geometry, and holds its exposure to external ultraviolet light as a boundary condition set by the cap. With the disk and its launching of outflows resolved, the path can move one step outward in process, while remaining within the same region, weighing how the combined radiation and mechanical feedback from the cluster and from the newborn objects carve, compress and disperse gas along the rim and in the pillars, and how those effects set the balance between the birth of new stars and the clearing of the cloud in this segment of the Eagle Nebula. Radiation and winds from the cluster, together with the narrow outflows from young objects inside the pillars, act in concert to reshape the rim and to decide how long dense gas survives there. Ultraviolet light creates and maintains the ionized cavity. It heats the boundary drives photoevaporation from exposed faces and sets the pressure that pushes compression waves into the cloud. Stellar winds from the most massive members of the cluster add a second mechanical component. They collide inside the cavity and inflate pockets of very hot thin plasma that fill corners the photons alone do not reach. The hot pockets leak through gaps and carry momentum to the rim, stirring the shell and writing small shocks that slip under bright arcs. On smaller scales, the bipolar jets from newly formed stars inside the shadow punch narrow tunnels through their envelopes and into the cooler interior, where they strike knots and lift thin shells that glide along the pillar axis. These mechanisms operate across different volumes and timescales, but share a single effect at the interface. They remove gas from some places, compress gas in others, and change the balance between collapse and dispersal, one small region at a time. The ultraviolet field governs the broadest share of the feedback. Each energetic photon that reaches the boundary strips an electron from hydrogen and leaves heat behind. The warmed gas expands and flows away from the surface at a few kilometers per second, carrying mass into the cavity. Where the field is strongest, caps thin quickly. Where dust or depth modulates the field, caps endure and move inward more slowly. The net mass loss from a rim segment is proportional to the illuminated area and to the photon rate that arrives there, and it is moderated by how often fresh material spills into the same segment from the cloud's filaments. In a pillar ensemble, shadows and bright patches arrange themselves in a patchwork controlled by local geometry. Tapered spires that stand proud of the rim receive more light per unit area, and therefore erode faster, while recessed shoulders that sit in partial shade erode more slowly, and sometimes gather material shed from nearby protrusions. Winds thicken the story by adding pressure without relying on direct line of sight. The most massive cluster stars vent supersonic flows that crash into one another and into the inner wall of the cavity. Collisions heat small volumes to temperatures of many millions of degrees Celsius. The resulting pressure domes expand until they find channels through which to vent. Where they meet the rim at oblique angles, they drive shallow shocks into the shell and energize the evaporative stream without lifting much mass. Where they find a weak patch, they push through and carve a new opening that later becomes a stable exhaust for the cavity as a whole. The spatial distribution of these impacts changes slowly as the cluster evolves. As stars move within the cluster and as individual winds wax and wane, the impact points drift across the interior, and the rim brightens in different places over time, giving the shell a flicker that rides atop the steady glow of photoionization. The jets from newborn stars supply the most focused mechanical feedback. Each jet carries a narrow beam of momentum along the local rotation axis, usually close to the pillar's length. In the protected interior, the beam remains collimated and deposits energy at a series of knots where it strikes denser clumps. These knots inflate small bow shocks that move away from the source at speeds of a few kilometers per second, slow enough that they remain visible for years when high-resolution images are compared. At each bow, gas is compressed and then cools, creating a thin, curved sheet that can later fall back along the pillar axis or slide sideways into the evaporative breeze. The cumulative effect of many small jets is to maintain a low level of turbulence in the pillar interior and to clear narrow lanes around embedded sources, helping accretion continue along the midplane while opening paths for radiation to escape along the poles. Radiative and mechanical agents sometimes cooperate and sometimes counteract. A wind-driven shock that reaches a cap may briefly amplify the pressure at the front, helping a marginal clump cross the threshold into collapse by raising its central density without raising its temperature. A jet-driven bow that passes under a cap can push material sideways, exposing a denser knot that then develops its own protective rim and begins to evaporate. Conversely, radiation can undercut the effect of a jet by thinning the envelope around a source and weakening the collimation near the base, turning a tight beam into a broader flow that couples less effectively to the dense interior. In these combinations, timing matters. A clump that has already begun to collapse can withstand a passing disturbance and keep contracting. A clump that is still marginal may be stirred back toward balance, or stripped of the very layer whose weight would have helped it proceed. Feedback also acts at the scale of the corridor. The cavity vents toward lower density surroundings through one or more breaks in the shell. Through these breaks, ionized gas streams into the arm and lowers the interior pressure slightly, which in turn slows the advance of the front against the densest walls and lengthens the lifetime of pillars that stand on those walls. The vented material spreads as a warm, thin plume that mixes with the diffuse gas along the arm and may, far from the cluster, contribute to the pressure that compresses other clouds, where the arm's flow converges. In this way, energy released in one scene can influence conditions in a neighbouring scene along the same lane. The influence is gentle and statistical rather than sharply causal, but over many millions of years it helps maintain the average pressure level that young clusters encounter when they form. On intermediate scales, the rim develops a network of thin shells and arcs where different feedback agents meet. Ionization fronts slow shocks from pressure waves, and the curved sheets left by jet bows intersect in patterns that, viewed in projection, resemble ladders and rings. The rings are not complete circles. They are cups and bowls seen at angles. Each cup traps a little more gas than its surroundings, and each has a slightly higher chance of hosting a dense core if the external pressure endures. The statistics of such cups and beads along a rim reveal the balance of forces. A rim dominated by smooth photoevaporation shows long continuous arcs with few beads. A rim stirred by winds and many embedded jets shows more frequent breaks and a higher density of small knots. The Eagle Nebula's rim exhibits both behaviours in adjacent stretches, consistent with a cluster whose most massive stars are not centrally concentrated, and with pillars that host several embedded sources each. Feedback determines how long the molecular reservoir remains near the cavity. Photoevaporation removes mass from the surface at a rate that rises with exposure. Winds and shocks accelerate removal in bursts by lifting sheets of gas that then disintegrate in the cavity. Compression increases the rate at which part of the gas becomes dense enough to form stars competing with removal. The net star formation efficiency along a rim therefore depends on how long compression persists, compared with how quickly erosion eats the supply, and on how many cores cross the threshold before their caps peel away. Because the brightest drivers, the most massive cluster stars, live only a few million years' time is short. If collapse needs long, quiet intervals, the efficiency remains low. If the rim already holds many near-critical clumps when the cavity lights the same external pressure, can help several reach the threshold in a short span. The chemical consequences of feedback appear in the boundary layers. Ultraviolet light breaks apart fragile molecules and charges small grains. Shocks briefly heat gas in thin stripes, sputtering atoms from grain surfaces and releasing species that had been frozen in ice. Mixing layers at the edges of cavities blend ionized gas from the interior with neutral gas from the shell, creating zones rich in simple ions and radicals that cool efficiently. As these layers cool, they recombine and feed the photodissociation skin with fresh atoms and molecules. The cycle repeats wherever a cap moves into new material. The repeating chemistry marks the path of the front and helps recover the three-dimensional shape of the rim, because different transitions brighten in different layers and at different depths along a given line of sight. Magnetic fields mediate how feedback shapes structure. A field aligned with the pillar axis allows compression to focus along that axis while resisting sideways shear, helping columns remain narrow and tall. A field that bends across the rim can stiffen the thin layer and delay the growth of corrugations, reducing the number of beads and favouring smooth arcs. Where jets run parallel to the field, their beams remain tight and their bows are symmetric. Where jets run across the field, their shocks thicken on one side and thin on the other, leaving slightly skewed cups and offset chains of knots. Polarization maps of dust emission in and around the Eagle pillars show ordered fields with gentle bends that conform to these expectations, supporting the view that feedback reads and writes the same magnetic pattern. The energy budget shared among radiation winds and jets evolves as the cluster ages. Early on, radiation dominates as the ionized volume grows toward equilibrium. Winds strengthen as the hottest stars reach steady output, then vary as those stars shift positions and as their interactions change. Jets are strongest per source at the youngest ages, and weaken as accretion wanes, but the number of jet sources can increase as more cores cross the threshold, keeping the total jet power roughly steady for a time. Later, as the most massive stars die, the photon supply declines, and recombination wins ground, dimming the cavity, unless other bright members take over. A single supernova adds a short, strong impulse that rearranges the rim locally and can open a new vent through the shell. On the longer timescale, removal by photoevaporation accumulates, and the molecular face recedes, leaving fewer pillars to host further collapse. Across all of these processes, the frame remains the same. Feedback modifies the surface that the spiral arm and the parent cloud supply. It acts through light pressure and narrow beams that redistribute mass at the rim, and it does so under ambient conditions set by the corridor's density, turbulence, and magnetic field. It neither guarantees nor forbids star formation. It tilts the odds in ways that depend on column density, on geometry, and on timing. In the Eagle Nebula, the mixed appearance of shrinking globules, bright caps with embedded sources, and long smooth arcs without cores reflects this balance. With the combined feedback now weighed at the interface, the path can narrow to timescales and life cycles. The next inward step keeps the region fixed and sets the clock how long pillars persist, how quickly cores assemble and dissipate, how long disks accrete under external light, and how rapidly the nebula's bright phase gives way to a fainter remnant once its most massive stars are all expressed within the same corridor, under the same pressure, and with the same careful pace from larger patterns to smaller outcomes. Time in the Eagle Nebula passes on several clocks at once. The largest clock belongs to the spiral arm, which carries clouds for many tens of millions of years along its ridge. Within that span, a shorter clock governs the bright phase of an ionized cavity, lasting a few million years from the moment the first massive stars switch on until their light declines or their lives end. Nested within that still shorter clock set the rise and fall of pillars, the compression and dispersal of dense rims, the slow inward motion of cores, the growth of protostars and their disks, and the flicker of jets that run for only a small fraction of a million years before fading. Each clock leaves a signature on the scene where arcs remain smooth, where columns thin, where globules darken, and where small sources warm a pocket inside their envelopes while the cap retreats across the face. A pillar's lifetime begins when the advancing front meets a clumpy wall and sculpts protrusions around the densest pockets. The first recognizable trunk appears as strong shielding builds behind a bright curved cap. From that moment, the column's length and width evolve under two rates that rarely match for long: the gain of mass along the axis from the protected interior and the loss of mass from the cap by photoevaporation. Where the root filament is thick and aligned with the magnetic field inflow can hold pace with loss, for a time keeping the trunk broad while the cap retreats. Where the root is thin or cut by older gaps, the trunk narrows steadily. In either case, the distance the cap travels during the cavity's bright phase is measured in a fraction of a light year to a few light years enough to expose embedded knots that were once deep within the wall. In practical terms, a prominent pillar remains recognizable for a few 100,000 to about a few million years before tapering into detached globules and then into nothing more than a ragged edge. Dense cores behind caps follow a slower rhythm at first and then a faster one. Before collapse begins, a core can linger near balance for hundreds of thousands of years, while external compression raises its density at roughly constant temperature. Once the threshold for instability is crossed, the inner regions contract on the local freefall time, which at the measured densities is only tens to a few hundreds of thousands of years. The outer envelope continues to feed the center for longer as it drains inward. This two-step pace explains why a pillar can host in close proximity a starless core just beginning inward, drift another further along that already hides a faint central source, and a third that has carved a small bipolar cavity, all while the cap continues to inch into the trunk. The outcome in each case depends on whether the interval of raised pressure endures long enough to carry the core through the slow stage into the faster one, before erosion removes too much mass from the illuminated face. Protostars mark time by accretion. Their brightest growth occurs during episodes when their inner disks dump mass onto the centre faster than average. Each episode lasts from a few years to a few thousands of years, and leaves a warm imprint on the inner envelope that later cools. Between bursts, the disk refills from larger radii and from the envelope. On a longer clock of order, a few 100,000 years, the envelope thins as the outflow opens wider cones along the poles and as the illuminated face evaporates. The system then appears as a compact star with a disk and a bright reflection cavity, while the midplane remains opaque. External ultraviolet light shortens the total time available for this evolution by lifting additional gas from the disk surface. In pillars that face a strong field, outer disks erode faster, and accretion ends sooner than it would in quieter clouds. In pillars that sit deeper in shadow disks persist longer and feed the centre for more of the cavity's life. Jets and broader winds keep their own brief schedule. A jet knot crosses 1/10 of a light year in only a few tens of thousands of years. Multiple knots launched in sequence trace the engine's variability over similar spans, and their bow shocks compress small pockets that cool in years to centuries before merging back into the pillar's interior flow. Because jets are strongest when a source is youngest, a pillar's inner turbulence is often most active just after the first embedded objects turn on, then settles as envelopes wane and the number of active outflows declines. The combined mechanical energy from many such sources is modest compared with the cluster's radiation and winds, yet over a few 100,000 years it imprints narrow channels and slight brightening along the pillar axis that persist until the cap has moved far away. The cavity's bright phase is defined by the lifetimes of the most massive stars in the cluster. Those stars live only a few million years. While they shine, their ultraviolet photons maintain the ionized volume, and their winds sustain hot pockets inside it. As one after another reaches the end of its life, the photon budget falls. Recombination begins to win ground, emission lines fade, and the shell's advance slows or halts, except where momentum already in the gas continues to carry it forward. A single supernova injects a short, strong impulse that can open a new vent, stir the rim into a fresh set of shallow shocks, and sweep some pillars into sheets. The shock's passage is fast compared with the cavity's age, but the channel it leaves can persist for the remainder of the bright phase, and set a preferred direction for the outflow of ionized gas into the arm. Star formation efficiency along the rim, how much of the nearby molecular reservoir becomes stars before dispersal, turns on the relative lengths of 3 times the duration of sustained compression at the interface, the time for many near-critical clumps to cross from balance into collapse, and the time for erosion to eat back the supply. If compression endures for about 1 million years or more, and if many clumps were already close to the threshold, when the cavity lit a greater fraction of the surface layer can complete collapse. If compression arrives late or in short pulses separated by long lulls, fewer cores finish the slow stage, and the surface becomes a gallery of evaporating globules with only scattered embedded sources. Observations of the Eagle Nebula show both regimes side by side, stretches with chains of young objects just behind bright caps, and stretches where the rim is sculpted yet bare of embedded sources, a juxtaposition consistent with a patchy history of pressure and with a varied initial distribution of dense pockets in the wall. Disks and small planetary precursors carry the longest small-scale clock that still fits inside the bright phase. In deep shadow, a disk can persist for a few million years, enough time for grains to grow settle and begin to form larger aggregates in the midplane. Exposure shortens that span by lifting gas from the outer layers and by heating the surface where small solids drift and collide. The difference can be read in populations across a cluster by counting how many objects retain thick outer disks near bright rims versus deeper in protected lanes. In environments like the Eagle Nebula, that count generally declines with increasing exposure, suggesting that external light trims the longest stages of gas-rich disks even while inner accretion continues for a time. The parent molecular reservoir keeps pace with these changes, while pillars' thin inflows along filaments can replenish the layer behind the rim. That inflow is slow compared with the speed of evaporation from the cap, but steady on the scale of 1,000,000 years. If the cavity's pressure weakens as bright members age, inflow can catch up locally and rebuild a piece of the wall further from the cluster. Conversely, if the cavity vents efficiently and maintains pressure, despite aging, inflow fails to accumulate, and the interface retreats into lower density terrain where pillars no longer form and only smooth arcs remain. In this way, the broad appearance of the rim at any moment reflects the balance of a slow supply clock and a faster removal clock. The end of the bright phase does not end the story of the gas. As radiation fades, the cavity recombines and cools. Thin shells and remnants of pillars sink back into lower pressure surroundings. Some dense cores that were midstream continue to collapse now without strong external erosion on their illuminated sides. Others disperse as support overwhelms the last push. Over several million years, the region transitions from a sharp-edged high-contrast nebula into a more diffuse complex of older stars and cool filaments. The younger stars remain reddened and show evidence of disks for a while, then clear their surroundings with their own outflows and radiation. The cluster as a whole relaxes dynamically as members drift, some escaping into the wider arm, while others stay bound if the stellar mass fraction is high enough to hold them. Viewed against the arm's slow drift, these nested life cycles repeat along the corridor. A different complex lies upstream, just entering its bright phase. Another lies downstream, already fading. The pressure level sustained by many such scenes at different ages helps set the average conditions in the arm and influences how the next generation of clouds assembles. The Eagle Nebula's present combination of long columns, active rims and embedded sources places it in the middle of this sequence rather than at the beginning or the end. Its pillars still stand tall enough to shelter cores and disks, its cavity still shines brightly, and its rim still carries cups where new seeds can gather, yet signs of thinning and venting already mark the path toward a quieter remnant. The timescales summarized here remain approximate because each depends on local density, geometry, and exposure, and because the zone of avoidance along the galactic plane and the bright background of the cavity limit some measurements. Even so, the relative ordering is secure. The arm's pattern persists longest. The cavity's light endures shorter. Pillars live shorter still. Cores cross their thresholds on shorter spans again. Bursts of accretion and knots in jets play out faster than that. Each shorter clock ticks inside the longer, and the combined effect is a steady rearrangement in which some material turns into stars, while the rest returns to the diffuse medium and flows on along the arm. Keeping the frame fixed, the narrative now has the duration of the scene and the pacing of its parts. With time set, the path can stay within the same region and shift windows rather than scales, comparing how optical, infrared, sub-millimeter radio and X-ray views each reveal a different layer of the pillars, the rim and the cavity, and how combining these windows resolves what the eye alone cannot separate in a single band. Different windows on the sky reveal different layers of the Eagle Nebula's structure, each sensitive to a specific range of temperatures, densities, and particle energies. In visible light, the bright rim and the inner cavity stand out through narrow emission lines from warm ionized gas. Hydrogen produces a strong red line that draws the contours of the shell. Oxygen and sulfur add green and blue lines that trace zones of higher or lower excitation. Stars in front of the nebula appear sharp and unreddened, while stars behind it are dimmed and reddened by dust. The pillars themselves show as dark silhouettes where their cold, dense interiors absorb background nebula light. Within these silhouettes, small round patches appear even darker, compact knots near the caps and small disks seen edge on where embedded young objects block the glow behind them. The visible map thus emphasizes edges and shadows. It outlines the surface where ionization meets neutral gas, and it shows the geometry of the cavity in projection, while concealing most of the mass that lies a little deeper in the cloud. Near-infrared light steps past much of the intervening dust. At these wavelengths, the glare of the ionized skin fades and warm dust on the rim glows softly. Embedded stars that are invisible in visible light emerge as faint reddened points, some surrounded by small reflection cavities lit by their own scattered light. Emission from molecules that survive in the photodissociation layer, such as hydrogen, in excited states writes thin filaments along the pillar faces where far ultraviolet photons penetrate without fully ionizing the gas. The pillars no longer appear fully black. Instead, they show internal texture, where half-hidden sources, warm dust fronts, and small cavities mark the path of compression and erosion within the first fraction of a light-year behind the caps. In this band, the three-dimensional relationships among cap, trunk, and shadow become clearer, because extinction is weaker, allowing sightlines to pass through more of the structure without being fully blocked. Mid-infrared images emphasize warm dust and complex hydrocarbons in the transition layer. Small grains and aromatic molecules absorb ultraviolet photons and re-radiate at wavelengths of a few micrometers to a few tens of micrometers, painting the rims as bright ribbons and outlining channels where radiation leaks between columns. The photodissociation layer appears as a continuous skin draped across the cap and flanks, with brightness variations that track both local density and local photon flux. Compact embedded sources show their envelopes and small outflow cavities in these bands. Disks seen edge-on become narrow dark lanes cutting across small reflection nebulae, while disks seen at an angle produce bilateral glows that bracket a dim midplane. The mid-infrared view thus highlights the chemical and thermal boundary, where molecules survive but dust is warm, and it identifies the youngest sources that have punched small windows into their envelopes, yet remain invisible at shorter wavelengths. Far infrared and submillimeter maps trace the cold backbone of the pillars and of the parent cloud. Dust, only a few tens of degrees above absolute zero, emits strongly at these wavelengths. The emission rises with column density, so the brightest far-infrared ridges mark where the trunks are thickest, and where filaments feed the bases from the interior cloud. The background nebular glow that complicates shorter bands fades to a faint sheen, and the mass distribution becomes clearer. Within the trunks, peaks in sub-millimeter brightness identify dense cores, some still starless, and others already warmed slightly at their centers by hidden protostars. The width of filaments and the spacing of cores along them can be measured in these maps, giving direct tests of how compression and magnetic support partition the gas into strands and seeds. Because extinction is weak at these wavelengths, the coldest regions that are entirely black in the visible become the brightest features, allowing a mass-weighted portrait of the pillars independent of their illuminated edges. Radio observations extend this view by separating gas phases through spectral lines. Atomic hydrogen emits a line that traces diffuse neutral gas on large scales, outlining shells and channels around the cavity, and revealing kinematic patterns that show how the ionized interior vents into the arm. Carbon monoxide and its rarer isotopic forms trace molecular gas at a range of densities. Maps of these lines reveal the long filaments that run into the pillar bases and the gentle inflows along their axes. High-density tracers such as lines from ammonia carbon, monosulfide and other molecules that require crowded conditions to shine pick out compact cores behind the caps. Line profiles give temperatures through relative intensities and give motions through small shifts in wavelength. Infeller symmetries in selected lines signal slow inward drift in cores, while narrow high-speed components along particular axes betray the presence of gentle molecular outflows from embedded sources. Together, the radio lines produce a velocity-resolved map of the cold interior that the infrared bands locate by brightness alone. X-ray observations add the hot end of the spectrum. Inside the cavity, collisions among fast stellar winds heat pockets of plasma to temperatures of many millions of degrees Celsius. These pockets glow in soft X-rays. Where the hot gas reaches the inner wall of the cavity, faint X-ray arcs can appear along segments of the rim, marking places where wind pressure adds to photoionization in stirring the shell. On smaller scales, shocks at the bases of fast jets and shocks where jets strike denser clumps can produce very weak X-ray emission that sits atop brighter infrared and visible features. Although sensitive measurements are required to separate these faint sources from the bright background of stars along the galactic plane, the detected emission confirms that both radiation and mechanical energy act in the interior and at the interface, each occupying its own temperature range and volume. Polarization across several bands introduces the magnetic field. In the far infrared and sub-millimeter aligned dust grains emit polarized light, with orientations perpendicular to the local magnetic field. Maps of this polarization reveal field lines that run along the pillar axes and bend gently around dense knots. The pattern shows that magnetic tension supports the columns against lateral compression and guides flows along their lengths. In scattered near-infrared light polarization vectors in small reflection cavities around embedded sources trace the geometry of their outflows and disks, adding an inner alignment to the outer one. These measurements connect the dynamics seen in gas and dust to the invisible framework that shapes them, and help explain why pillars remain slender even under strong external pressure. Time adds a final dimension to these windows. High-resolution images taken years apart in visible and near-infrared bands show small changes along bright rims and within filigree corresponding to motions of order, a kilometre per second. Comparisons of far infrared and sub-millimeter maps across similar intervals reveal shifts in the balance of brightness, where caps recede and where new layers of dust are exposed. Radioline surveys repeated after long baselines catch subtle variations in line shapes that track the advance of slow shocks into the trunks. While each effect is small together, they turn still images into a slow film that tests models of photoevaporation, compression, and jet propagation under conditions set by the cluster and the arm. Combining the windows yields a layered reconstruction. The visible map outlines the ionized boundary. The near and mid-infrared maps reveal the photodissociation skin, the warm dust on the face, and the younger sources breaking through their envelopes. The far infrared and sub-millimeter maps expose the cold mass that supports the pillars and locate the cores that gravity is gathering. The radio maps measure motions in those cold layers and specify where inflow and outflow occur and with what speed. The X-ray map shows where the hottest gas from winds and shocks adds pressure. Polarization ties them all to the magnetic field. Taken together and placed in 3 dimensions through kinematics and extinction, these data show a cavity that breathes through a few vents a rim that advances in a ragged contour, set by both density and light, and pillars that persist where roots are thick and fields align with the axis. They also show a population of embedded sources arranged in chains behind caps, each with a disk and a narrow outflow, whose small cavities intersect and grow within the larger shadow. Each window carries limits that must be respected. Visible light suffers heavy extinction near the plane and sees only surfaces. Infrared bands can be confused by bright foregrounds and by heated dust that is not close to the pillars. Sub-millimeter maps rely on dust properties that vary with environment and must be calibrated against independent measures of column density. Radio lines require careful modelling of excitation to convert brightness into mass and can become optically thick in the densest peaks. X-rays are faint and hard to isolate in a field crowded with stars. Polarization requires enough ordered grain alignment to overcome noise and can be altered by changes in grain properties near strong radiation fields. The strength of the combined view lies in cross-checks that exploit the fact that different bands respond to different physics. A dense core identified by sub-millimeter brightness should have narrow high-density radio lines and should appear as a cold dark patch in the near-infrared against a bright background. A cap that looks bright in visible lines should glow in mid-infrared bands and should show adjacent radio signatures of carbon in low ionization states. Hot pockets detected in X-rays should correspond to places where winds collide, and those places should sit inside the ionized volume and near optically bright stars. The multi-wavelength picture thus does more than add detail. It orders the scene by depth and temperature and motion. It places the Eagle Nebula within a corridor of the spiral arm, locates the cavity inside that corridor, climbs the pressure ladder, from hot wind pockets to warm ionized gas to the thin photodissociation skin, and then descends into the cold trunks and cores that support the pillars. It shows where gravity is winning quietly, and where erosion is winning slowly, and it traces the narrow paths along which newborn objects return momentum and heat to their surroundings. With these windows aligned, the narrative can turn to what remains uncertain, and how measurements constrain those uncertainties, keeping the frame, the pace, and the scale unchanged, while marking the limits of distance efficiency and feedback balance that observations still leave open. Several measurements that frame the Eagle Nebula remain uncertain, and those uncertainties shape how securely each physical inference can be drawn. Distance sets the global scale. The nebula lies toward the galactic plane, where dust is thick and where star fields are crowded. Parallax measurements for cluster members improve the estimate, but still carry systematic errors from extinction unresolved binaries and small calibration offsets. The result is a distance known to within a margin that spans several hundred light years. That margin propagates into every absolute quantity: pillar lengths, cavity size, core masses, and jet speeds. Relative patterns remain robust because they depend less on the absolute scale, but any statement that requires mass or energy in physical units must carry the same fractional uncertainty that the distance imposes. Ages for the central cluster and for the embedded population carry complementary ambiguities. The brightest cluster members fix a young age of only a few million years, when their colours and luminosities are compared with standard evolutionary tracks. Crowding variable extinction and unresolved companions bias those placements on the tracks. Embedded sources behind the rim show spectral energy distributions that rise into the infrared and imply even younger stages, but the same dust that hides them also reshapes their apparent colours. Without exact extinction for each line of sight, the stage of an individual source remains bracketed rather than pinpointed. As a result, the claim that a given pillar hosts a sequence from starless core to protostar to disk is secure in pattern, but still imprecise in absolute timing. Star formation efficiency is central to the life cycle of the rim, yet is among the least certain numbers. Converting molecular line brightness into total mass requires an assumption about the abundance of the tracer relative to hydrogen, and about how well the tracer is excited. Both depend on local conditions. Dust-based masses require an emissivity that varies with grain composition and size, and a temperature that is rarely uniform along a line of sight. Ranges chosen for these properties can alter the inferred gas mass by a factor of a few. On the stellar side, counting young sources depends on completeness, limits that change with crowding and with background brightness. Small disks seen edge-on can be missed, and faint sources buried deep in the trunks escape detection. When both sides are uncertain, the fraction of gas converted into stars before dispersal remains a range rather than a tight value, though the qualitative result that most gases return to the diffuse medium still holds. The balance between feedback that reveals pre-existing dense structure and feedback that truly triggers new collapse is another open question. A dense knot that forms inside a converging flow before the cavity lights can later be uncovered by the advancing front and can be mistaken for a triggered core. Conversely, a marginal clump pressed by the front can cross the threshold only because the external pressure persists. Disentangling these cases requires velocities for the gas and ages for the embedded sources with enough precision to order events. Line profiles give expansion and inflow speeds to within a small fraction of a kilometre per second, when the lines are bright and simple, but confusion from overlapping components along the plane and optical depth in the most common tracers limit accuracy. Source ages carry the dust-related uncertainties already noted. The conclusion is cautious. Both exposure and true triggering occur along the rim with their relative importance, varying from one column to the next. Three-dimensional geometry is hard to recover from two-dimensional projections. A pillar can lean toward or away from the observer, and its cap can sit at a slant to the front. brightness contrasts that appear to signal density. Differences can also be caused by tilt, because a slanted face presents a longer path length of ionized gas, or a thicker skin of warm dust to the line of sight. Kinematic maps help, but do not fully remove this ambiguity, because multiple flows overlap in velocity as well as in position. Even when the sign of motion is clear, the inclination remains uncertain, without an independent handle on the full vector. As a result, statements about the exact thickness of the photodissociation layer or the exact curvature of a cap carry hidden dependence on geometry. Magnetic fields are measured indirectly and with limited resolution. Polarization of dust emission traces field orientation in the plane of the sky, but not strength. Estimating strength from the dispersion of polarization angles requires assumptions about turbulence that are only approximately met. Zeeman measurements of certain radio lines can provide line-of-sight strength in select locations, but the lines are weak, and the background is bright toward the galactic plane. The combined picture of an ordered field aligned with many pillars is well supported, yet the exact magnitude of magnetic support within a given trunk and the degree to which the field moderates specific instabilities at the cap remain only loosely constrained. Chemical diagnostics depend on models that balance heating, cooling, and reaction pathways. In the transition layer where molecules are broken by far ultraviolet light, but gas remains mostly neutral line ratios from carbon, and oxygen respond to density and to radiation field strength. Those ratios also respond to microphysics of grains that is not uniform across the rim. Grain sizes change under strong radiation. Surface properties change as ice mantles are deposited and removed. These changes alter heating efficiency and the coupling between gas and dust. When the same region is modelled with different grain assumptions, the derived densities and radiation fields shift within the bounds allowed by the observations. Thus, the broad result that the layer is thin and dense is secure